Hello, welcome to our Cisco CCNP S-Core video course. On this lesson, we're going to explore about the following topics, covering security concepts, common on-premises threats and attacks, common cloud threats and attacks, and common security vulnerabilities. So, information security is the safeguarding of data in information systems against unauthorized access, use, disclosure, disruption, alteration, or destruction in order to maintain confidentiality, integrity, and availability. Information security does not really refer to a specific security technology. Rather, it refers to a strategy that includes the people, right, processes, policies, and technologies needed to identify, prevent, document, and mitigate the myriad risks that exist today. So here on this course, you should be familiar with the information security principles and terminologies. So the procedures and technologies you implement must ensure three things in order to provide adequate protection for network resources. First one is data confidentiality, right? So data confidentiality ensures that sensitive information can only be viewed by authorized users. Next is integrity. So data integrity ensures that sensitive information can only be changed by authorized individuals. Data authenticity may be ensured by using integrity. Next is availability. So system and data availability ensures that authorized users have continuous access to critical computing resources and data. So in today's security environment, the need for network security is influenced by business goals and risk management. In other words, risk assesses the potential for threat vectors to exploit the vulnerabilities of the assets you're attempting to safeguard. Now, let me explain a few key terms that is being used in the field of information security. The first one is asset here, right? So an asset is anything that adds value to a company, right? Information or computer systems, for example, could be considered as assets. You can more effectively determine the time, effort, and money to spend in securing assets if you know the assets you're trying to protect, as well as their value, location, and exposure. The next concept is vulnerability. So a vulnerability is a flaw in a system or its design that a threat can exploit. Vulnerabilities can sometimes be found in the protocols themselves, such as TCP/IP, right? This one. Vulnerabilities are frequently found in operating system and also in applications. Now, any potential danger to assets is considered a threat. Okay, put it here, threat. Someone or something identifies a specific vulnerability and exploits it, resulting in exposure, which is when a threat is realized. The threat is latent and has not been realized if the vulnerability exists theoretically but has not been exploited. The threat agent or threat vector is the entity that takes advantage of a vulnerability. And the third important principle is countermeasure. A countermeasure is a safeguard that reduces the risk of an occurrence. A countermeasure reduces the likelihood of a threat agent successfully exploiting the risk by either eliminating or reducing the vulnerability. Now let's talk about vulnerability assessment. So at least in the context of information security, a vulnerability is a flaw in software, right, or hardware that is paired with an exploit as a means of exploiting that flaw. The security team of an organization's network and information systems must keep up with the latest security vulnerabilities and meet threatened network and information systems. So here, as you see, right, this table summarizes some of the activities that occur during the vulnerability assessment process. The first part is device discovery. So here, there's going to be various methods that are being used to identify the servers, appliances, and other network devices during this particular phase. Next is a service enumeration. So here, a vulnerability scanner tool identifies the ports and services available to each discovered system, such as email and web servers. Third is scanning. So here, right, a port scan is performed by the vulnerability assessment tool to determine what services are running on each active device. Determined services will assist the vulnerability scanner in determining which types of vulnerability checks should be performed on a given port. All hosts are scanned after the port scan to find vulnerabilities such as server misconfiguration, missing patches, and dangerous services. And the fourth part is called validation. So some of the problems discovered by a vulnerability scanner may be false positives, and these issues may be legitimate in some cases, but they may not be relevant in others due to compensating controls that the vulnerability scanner cannot account for. Now let's talk about common on-premises threats and attacks. So viruses, ransomware, rootkits, worms, Trojan horses, backdoors, covert channel tools, spywares, and advanced persistent threats are examples of malicious software or malwares. Malware can harm your computer in a variety of ways, including displaying messages, causing programs to malfunction, encrypting files, and demanding a ransom to decrypt them, and even destroying data or hard drives. So here, let's talk about viruses and worms first, right? So viruses are different because they're typically infect host, program, or file. Viruses require some form of human action. Now, what is a worm? A worm can travel between systems without human assistance. When a worm executes, it can infect many more systems. Consider an example. A worm can email itself to everyone in your address book, and this process is repeated on each computer it infects. That much traffic can cause denial of service, right, in no time, or DOS. So viruses and worms are similar to a spyware. Okay, put it here. Spyware. So malicious software, right, is also being called as spywares. So many users don't know the program has been installed, and the program hides itself in an obscure location where it cannot be easily found. Cyber espionage intercepts and occupies system resources. Spyware can also redirect your web traffic and annoy you with pop-ups too. Users see spyware as another type of virus. So here, malware propagates through the computer world, right, in several basic ways, like in the master boot record, using bias infection, file infection, macro infection, cluster, and multipartite. Let's talk about another kind of infection, which is a Trojan, right, or a Trojan horse. So the wooden horse, right, that the Greeks used to infiltrate Troy is known the Trojan horse, right, like this one. It's a malicious piece of software that appears to be legitimate. Users are frequently duped into downloading and running it on their computers. It can perform a variety of attacks on the host once it has been activated, ranging from annoying the user by popping up different windows or changing desktops to damaging the host, like deleting files, stealing data, or activating the spreading of other malware such as viruses. Backdoors have also been known to be created by Trojans to allow malicious users access to the system. Okay, let me put it here. Backdoor. So Trojans, right, unlike viruses and worms, do not reproduce by infecting other files or by replicating themselves. Trojans must be spread by user actions, such as opening an email attachment or downloading and running a file from the internet. So to better understand what Trojans do, you have to refer to the following list, which outlines a few of these types. This can be remote access Trojans, or what we call as RAT, right? We have data hiding, e-banking, denial of service or DOS, proxy, using FTP, or using security software disablers. Now, the following are the common targets of Trojans, which includes credit card data, electronic or digital wallets, passwords, insider information, data storage, and advanced persistent threat or APT. Even after a hacker has created a Trojan, it must still spread it. It is a lot easier now than it used to be because of the internet. Malware can be spread in a variety of ways, including the following, like P2P networks, instant messaging, IRC, right? If you live in the 90s, you know this. Email attachments, physical access, browser and browser extension vulnerabilities, SMS messages, impersonated mobile apps, watering hole, and freeware. Now, let's talk about another type of attack, which is called DOS or denial of service attack. Okay. DOS attacks attempt to consume all the critical resources in order to render them unusable. Those attacks are considered a major risk because they can disrupt a business operation and are simple to conduct. So one type of a DOS attack is a TCP SYN flood attack. This is actually a very common denial of service attack. So a TCP flood attack exploits the TCP three-way handshake, right? So three-way handshake or HS by sending multiple TCP SYN packets with random source addresses to a target host. The victim host replies with the SYN ACK and adds an entry to the connection table. Then the SYN ACK destined for an incorrect or non-existing host will not be responded to, and the connection will stay in the tables until a timer expires. So when attacking systems using TCP, an attacker can fill up the connection table and deny services such as email, file transfer, and World Wide Web or www to legitimate users. The originator of the attack is untraceable because of the forged IP address. The next common kind or type of DOS attack is the ping of death. So ping of death attacks can crash systems, groups of systems, and services. Ping of death attacks specify a fragment with an offset that corresponds to a full packet size of 65,536 bytes or 65K. IP protocol specifies a maximum packet size of 65K as well, or 65,000 bytes. Now, receiving this type of fragment will cause the system to crash or reboot if the buffers aren't already set up. Ping of death exploits vulnerabilities in the IP layer, but similar attacks exploit vulnerabilities in the application layer, like SNMP, syslog, DNS, or other UDP-based protocol messages were also exploited by attackers. So here it is almost certain that if a message with incorrect syntax is sent, the system will crash and will be reloaded. So another kind of attack is called phishing. So phishing is a common form of social engineering, right? If you heard about this before. Engineering. So a phishing email, right? So like this one, a phishing email usually pretends to be from a large legitimate company. Then the target may have a real account with a large organization because it's legitimate. The malicious website closely resembles the legitimate organization's website. The goal is to obtain personal information from the victim, such as account numbers, social security numbers, usernames, and passwords. There are actually different types of phishing, right? So we have a couple here, which includes spear phishing, whaling, farming, watering hole, and smishing. So as part of the CCNP score, right, review, you have the opportunity to at least research for all of these terms and be familiar on what it do, well, what are the differences as well. Okay. Another type of attack that can be done to a network is called the rootkit. So once an attacker has gained control of a system, right? This one is the attacker. They may wish to conceal their work, such as files saved to a disk, backdoors installed, and network connections established like CNC or listening ports. So a rootkit, right, is actually a tool that hides these resources by integrating with the operating system's lowest levels. A rootkit is the most sophisticated tool that is available to an attacker. Its goal is to completely conceal the attacker's activities on the local system by compromising the system's internal structure. A rootkit can gain control of the operating system as well. A rootkit presents a sanitized version of the output when a program attempts to list files, processes, or network connections, removing any potentially incriminating information. So as I've said, right, rootkits can conceal um, not only attackers' activities, but also their own presence. Rootkits are, as a result, it's an area that is extremely difficult to detect. Defenders can use a trusted toolset to get around some of them, but this isn't always the case. If there's any indication that a system has been infiltrated by a rootkit, the operating system should be considered permanently compromised. The machine should be backed up for analysis purposes, then the hard drive should be wiped and everything should be reinstalled. Rootkits are also extremely difficult to create due to their complexity, right? So rootkits must consider operating systems, versions, architecture, and a variety of other factors. A user who upgrades their operating system or applies a patch may be able to undo the rootkit's work, or more likely cause the compromised host to crash. Because rootkits aren't widely available, they're only used by the most sophisticated hackers or attackers. The rootkit is used by the attackers within the organization and on multiple targets. Identifying and reverse engineering the rootkit could reveal the attacker's presence all over the world. So MITM attacks, sometimes referred to as eavesdropping attacks or connection hijacking attacks, exploit inherent vulnerabilities of the TCP/IP protocol at various layers. It is derived from packet sniffing and spoofing techniques and is completely invisible to the victims, making it very difficult to detect and stop. In MITM attacks, a system with the ability to monitor the communication path between two systems is introduced in that communication path. The main goal is to obtain the data being sent between two parties. TCP/IP, right, uses handshake, like it's sending control traffic, like just send, act, and act packets. So here, the three-way handshake, right, establish connections between two different network interface cards, which use packet sequencing and data acknowledgement to send or receive the data. Now, data flows from the physical layer all the way to the application layer. And here, MITM attacks, right, can be carried out on any layer of the network. So here are the examples of OSI layer MITM attacks, which includes the physical layer, right? So here you can just tap someone's physical connection and send all packets to the MITM. Next is data link layer, still part of the OSI. It uses ARP poisoning to cause victims to send all their packets to the MITM. Third is network layer, which can manipulate packet routing to route all the packets to the MITM. And session layer, and this MITM decodes and encrypts the HTTPS web traffic. To succeed, the victim's web browser must accept the certificate presented by the SSL TLS MITM, which could be done by the initial malware infection. And the last one is application layer, right? So because here we have what we call as browser hijacking, right? Which is typically a man in the browser attacks, or man in the middle browser attacks begin with a malware infection. Malware is injected into the web browser of the victim and it awaits them on the specific website. The malware takes action and asks the user to enter personal information on the web page. Malware often has different attack targets hard-coded into its code. So one of the well-known type, right, that is discovered before is Zeus. So we call it Zeus. So it focuses on the financial sector. So when this malware is activated, it may insert additional fields on the page to collect sensitive information or act as a keylogger to steal the data. So a user's web browser can't be trusted because it has been compromised. So some of the other additional MITM attacks include ARP poisoning, ICMP-based MITM attacks, DNS-based and DHCP-based MITM attacks. Let's talk about SQL injection. So, because databases, right, which often contain sensitive and valuable information are attractive targets, SQL attacks are very common. The SQL injection attack is one of the most common SQL attacks. Now, to detect if the relational database has been subjected to SQL injection attacks, you should be able to recognize suspicious SQL queries. So, an SQL injection attack involves inserting an SQL query into an application via the client's input data. The successful SQL injection exploit can read sensitive database data, modify database data, perform database administration operation, and in some cases, issue commands to the operating system. An application will be vulnerable to a SQL injection attack unless it uses strict input data validation. An attacker could use a malicious crafted input string to trigger an SQL injection attack if an application accepts and processes user supplied data without any input data validation. Now let's talk about cross-site scripting. So cross-site scripting, or XSS, is a type of a web-based command injection attack that involves injecting malicious scripts into otherwise safe and trusted websites. Other victims who visit the infected websites are then served the malicious scripts. The malicious script, for example, could steal all sensitive data from the user's cookies stored in the browser. The injection of malicious scripts into web pages that are executed on the client side in the user's web browser is referred to as XSS, right? Cross-site scripting. The malicious scripts can be used to gain access to a user's computer system or sensitive data, such as a session cookie. To implement the attack script, XSS can use JavaScript, Visual Basic Script, and other types of code. XSS is a security flaw in client-side scripting languages that causes a threat. Now, when a malicious user is allowed to post content to a trusted website without any input validation, XSS attacks can occur, and any other users who visit the trusted website will then be exposed to the malicious user's contents. So here are the following examples of XSS attacks. So the first one is stored, right? And the second one is the reflected. So let's talk about the stored first, or the persistent type of XSS attack. So stored XSS is the most dangerous because it remains in the XSS infected server indefinitely. When the victim visits the infected web page, the server sends the malicious script to them. Next is the reflected or non-persistent. So this is the common type of XSS, right? Which is called the reflected XSS. Unlike stored XSS attacks, which require the attacker to find a website that allows the malicious scripts to be permanently injected, reflected XSS attacks only require the malicious script to be embedded in the link. The victim must click the infected link in order for the attack to succeed. Reflected XSS attacks are usually delivered to victims through an email message or another website. Now, when a victim is duped into clicking on an infected link, the malicious script is reflected back to the victim's browser and executed. Reflected attacks can be avoided by vigilant users. So here are the following countermeasures for cross-site scripting, or XSS. First is deploy a DNS-based security like Cisco Umbrella, right? To block the users from accessing malicious website. You can also deploy a web proxy security solution such as the Cisco WSA or Cisco Web Security Appliance to block users from accessing malicious websites. You can also deploy an IPS solution to detect and prevent malicious XSS or CSRF. And you can also educate end users, like for example, how to recognize phishing attacks. Okay, now let's talk about common cloud threats and attacks. First, right, let's talk about the cloud benefits and why we're doing it. So to host their applications, many companies are moving to the cloud or deploying hybrid solutions. So when companies migrate to the cloud, they almost always want to move from the CapEx, right? So here, or capital expenditure, to an operational expenditure type of model, right? So a multi-cloud environment is used by the majority of Fortune 500 companies. Now, cloud computing security is without a doubt more important than ever, right? Because we're talking about the cloud. It's a shared environment. And many of the same features as traditional IT security are available in cloud computing security. And also, this includes safeguarding sensitive data against theft, data exfiltration, and deletion, as well as ensuring privacy. Now, the following are some of the benefits of using a cloud based service like storage that is distributed or distributed storage, resource pooling, scalability. It is accessible from anywhere, which is true, measurable services, and management that is automated. Now, the following are some examples of cloud deployment models, right? The first one is public cloud, right? So here is generally available to public, and is offered by third-party providers, and it's available to anyone, right? And it scales quickly and conveniently. Next is a private cloud. So private cloud is offered to selected users over the internet or a private internal network, provides greater security controls, and requires traditional data center staffing and maintenance. And the third one is called the hybrid cloud, which is a combination of both public and private cloud. It is a shared security responsibility between the public and private environment, and it helps maintain tighter controls over sensitive data and processes. So now let's talk about this, very familiar word like the X as a service, right? So which I know you heard about IS, PaaS, or SaaS, right? Let's talk about this one first. So the following are the three basic models of cloud computing. The first one is IS, okay, or infrastructure as a service. So here, um, IS is actually a cloud solution in which you rent the infrastructure itself. You buy virtual power to run your software when it's needed. This is similar to running a virtual server on your own hardware, except you're using a virtual disk instead of a physical disk. Because you only pay for what you use, this model is similar to that of a utility company. And as you will notice here, right, um, this part here are the only part that you rent from the IS provider. However, the customer will still need to manage the OS up to the application, right? Of course, here, if you look at the on-premise, the customer will own all of this one. This is the traditional way of managing these workloads in your own data center. Okay. Next is a PaaS, or platform as a service. PaaS. So PaaS takes care of everything except the applications, right? This one. This model can use application programming interfaces or APIs, website portals, or gateway software to provide services throughout the system development lifecycle or SDLC. These are usually proprietary solutions which can cause issues if the customers move away from the provider's platform. And the third one is SaaS, right? Or software as a service. SaaS is a package solution that is delivered as a service. The user is given access to the software on a rental basis. Typically, the service is delivered via a front end or web portal, while the end user can access the service from any location. The company is charged a per-use fee, right? So this is SaaS, where, all of these services is being outsourced to the public cloud provider. Now let's talk about cloud computing attacks. So cloud-based services are vulnerable to a variety of attacks because they're accessible via the internet, as more businesses adopt cloud computing and expect hackers to follow suit. The following are some of the possible attack vectors that criminals can use. First is session hijacking, right? So here, when an attacker sniffs and intercepts traffic in order to take over a legitimate connection to a cloud service, this is known as a session hijacking service or attack. Next is DNS attack. This type of attack persuades users to visit a phishing site and hand over valid credentials. Right? As we've studied before, we also know that there's an attack called the cross-site scripting or XSS. It is used to steal cookies that can be used to gain access to a cloud-based service as an authenticated user. Next is SQL injection. This attack takes advantage of flaws in cloud-based applications that allow attackers to send SQL commands to be executed on a database. Next is session writing. It's actually a term coined by the European Commission to describe a cross-site request forgery attack or CSRF. Attackers use this technique to send unauthorized commands through an active session by tricking users into clicking on a malicious link in an email while they are logged into a cloud service. Third is a DDoS attack. So according to some security experts, the cloud is more vulnerable to DDoS attacks because it is shared by many users and organizations, making any DDoS attack much more damaging. Next is man-in-the-middle attack, right? Or MITM. So there's also what we call as MITM or man-in-the-middle cryptographic attack. So when an attacker places himself in the middle of a communication channel between two users, he is committing a man-in-the-middle attack. The attacker has the ability to intercept and modify communication whenever he is able to do so. Next is side channel attack. So here, an attacker could try to compromise the cloud by positioning a malicious virtual machine near a target cloud server and then launching a side channel attack. Next is authentication attack. So here, authentication is a weak point, right, in hosted and virtual services and is frequently targeted. There are many ways to authenticate users, such as based on what person knows, has, or is. The mechanisms used to secure the authentication process and the method of authentication used are frequent targets of attackers. And the last one is API-based attacks. Here, APIs are frequently configured insecurely. API misconfigurations can be used by an attacker to modify, delete, or append data in cloud-based application and systems. Okay, now let's talk about common security vulnerabilities. So, as we discussed earlier, right, a vulnerability is a flaw, right, in the design implementation, software or code of a system, or the lack thereof. A vulnerability can take many forms, ranging from a flaw in system design to the implementation of an operational procedure. A vulnerability can be mitigated and the risk of exploitation is reduced by properly implementing safeguards and security countermeasures. Vulnerabilities and weaknesses are common owing to the fact that no software or code is perfect. Although some vulnerabilities have limited impact and are easily mitigated, many others have far-reaching consequences. Vulnerabilities can be found in the following, like in applications, right? Where software and applications, right here, it offers a wide range of features, right? The application. And it's possible that applications are set up for usability rather than security. It's possible that an application requires a patch or update, which may or may not be available. Attackers focusing on applications have a plethora of targets to examine, and considering all of the programs that are running on your computer at home or at work. Next is OS vulnerability or operating system vulnerability. So here, workstations and servers have operating system software installed, and attackers can look for flaws in operating system that haven't been updated or patched. Next is hardware vulnerability. So hardware can also be source of vulnerabilities, right? Patches to microcode or the firmware, as well as the operating system or other system software, may be required to mitigate a hardware vulnerability. Spectre, right, as you heard about maybe 2 years ago, there's a what we call a Spectre, and what's the other one? Meltdown vulnerabilities. I think this affects the CPUs, right? Especially for Intel, as far as I remember. So these are actually examples of hardware-based vulnerabilities. And these flaws take advantage of a feature known as speculative execution, which is found in modern operating systems. Next is a misconfiguration. The device or software configuration file and configuration setup may be configured or deployed in an insecure state. Open ports, vulnerability services, or misconfigured network devices could all be contributing factors. Consider the case of wireless networking, right? Now, is it possible to find any wireless devices in your neighborhood that aren't encrypted? The last one is shrink wrap software. So this is actually a program or an executable file that runs on a workstation or server. When installed on a device, it can provide a wealth of functionality as well as sample scripts or code. All right, now let's talk about code injection. So I'm sure you heard about or we discussed about some code injection attacks earlier, right? Like XSS and injection or SQL injection attacks. So here we're going to talk about or do a deep dive about what code injection is. So code injection vulnerabilities are exploited by forcing an application or a system to process invalid data. An attacker takes advantage of this type of vulnerability to inject code into a vulnerable system and change the course of execution. Successful exploitation can lead to the disclosure of sensitive information, manipulation of data, and denial of service conditions, and more. Examples of code injection vulnerabilities include SQL injection, HTML script injection, dynamic code evaluation, object injection, remote file inclusion, uncontrolled format string, and shell injection. So SQL injection, right? SQL flaws can be disastrous because they allow an attacker to view, insert, delete, or modify a database record or DB. In SQL injection attack, the attacker uses the web application to insert or inject partial or complete SQL queries. In order to execute predefined SQL commands, the attacker injects SQL commands into input fields in an application or a URL. Now, understanding when the application interacts with a database is one of the first steps in finding SQL injection vulnerabilities. Web authentication forms, search engines, and interactive sites like e-commerce sites are common examples. The following are the different types of SQL injection attacks, which include in-band SQL injection, out-of-band SQL injection, and blind or inferential SQL injection. So here, right, an attacker must write a syntactically correct SQL statement to perform an SQL injection attack or query. The attacker may also use error messages returned by the application to reconstruct the logic of the original query in order to figure out how to carry out the attack correctly. The attacker may have to reverse engineer as well the logic of the original query if the application hides the error details. So one of the types earlier, right, as I've said, is HTML injection. So when an authorized user gains access control or gains control of an input point and is able to inject arbitrary HTML code into a web application, this is called as HTML injection. A successful exploitation could result in the disclosure of a user's session cookies, which an attacker could use to impersonate a victim or change the web page or application content that the victims see. Cross-site scripting can be caused by HTML injection vulnerabilities. Now let's talk about command injection. A command injection attack occurs when an attacker uses a vulnerable application to try to run commands on a system that he or she is not supposed to be able to run. When an application does not validate data supplied by the user, command injection attacks are possible, like for example, data entered in web forms, cookies, HTTP headers, and other elements. Here, the data is sent to a system shell by the vulnerable system. Next is, so here, right, also an attacker uses command injection to send operating system commands to a vulnerable application, which then executes them with the vulnerable application's privileges. Code execution and code injection which involve exploiting a buffer overflow or similar vulnerability, are not the same as command injection. Now, the following are the most common ways to take advantage of authentication-based vulnerabilities in an affected system. This includes credential brute forcing, session hijacking, redirecting, exploiting default credentials, exploiting weak credentials, and exploiting Kerberos vulnerabilities. So let's talk about at least two, right, of the authentication-based vulnerabilities. The first one that I told you earlier is about credential brute forcing. So in a credential brute force attack, the attacker tries a variety of usernames and passwords to log into an application or a system. Brute force attacks are divided into two categories, right? First is online brute force attacks and the offline brute force attacks. So what's the difference? In this type of attack, the attacker tries many different combinations of credentials to log into the application directly. Because you can easily inspect for large numbers of attempts by an attacker, online brute force attacks are easy to detect. Now, the next one is offline brute force attack, right? So an attacker can gain access to encrypted data or hashed passwords using this method, and these attacks are more frequent. Online attacks are more difficult to prevent and detect, while offline attacks, on the other hand, necessitate significantly more computation effort and resources from the attacker. The next one is session hijacking, right? So that's the second one. So here, an attacker can hijack a session in a variety of ways, and the session token can be compromised in a variety of ways, which includes predicting session tokens, sniffing web session, man-in-the-middle attack, and man-in-the-browser attack. And the very last topic is about cross-site request forgery, or CSRF. So cross-site request forgery, or CSRF or XSRF, attacks occur when an application trusts a user and sends unauthorized commands to it. CSRF attacks differ from XSS attacks in that they take advantage of an application's trust in the user's web browser. One-click attacks or session writing are terms used to describe CSRF vulnerabilities. CSRF attacks are most commonly found in applications that rely on users' identity. Attackers can persuade a user's browser to send HTTP requests to a malicious website. A CSRF attack occurs when a user who has been authenticated by the application using a cookie stored in the browser unintentionally sends an HTTP request to a site that trusts the user, resulting in an unwanted action. Okay. All right. That's the end of the lesson. So here on this video, we covered the common security concepts that you have to be aware of. We discussed about the common on-premises threats and attacks, the common cloud threats and attacks, and the common security vulnerabilities. Thank you very much for watching the video. Hi, welcome to our Cisco CCNP ESCOR video course. On this lesson, we're going to explore what cryptography is and what are its components. So, with billions of people, right, communicating on it, which we call as the internet, right? The internet is the most efficient and widely used information highway for communication and information exchange. The security of its data traffic has also become one of the major concerns here. However, you can always use a VPN, right? Call it a VPN, in order for you to protect all of the traffic that passes through the internet. So there's another concept which we call as cryptography, right? Let me put it here. Cryptography should be an RPHY. Okay. So VPNs with cryptography can be used to provide privacy for data traffic on this, what we call as the information highway or the internet. Okay. So before you start using a VPN, you should have at least a solid understanding of what cryptography is. So here, cryptographic algorithms cryptographic protocols, and how cryptography provides important privacy services like confidentiality, integrity, and authentication should all be familiar to you. Now, a VPN is defined as a restricted use or logical or artificial or simulated computer network that is constructed from the system resources of a relatively public or a physical real network such as the internet, and often by using encryption, right, which is located at the host or the gateways, and often what we call as tunneling, okay, virtual network links across the real network, which is the internet. Now, a VPN can be defined in more detail as follows, right? So V, this means virtual, okay? So these are virtual networks, which are logical networks that are not bound by any physical architecture. Next is private, right? So private, it uses two methods to provide privacy. One is the non-cryptographic, and the second one is the cryptographic. It's non-C and the cryptographic. So when we say non-cryptographic, it's independent of IP addressing and routing schemes. Next is the cryptographic, which provides confidentiality, integrity, and authentication, which are all provided by cryptographic approaches. And of course, the last one is the network, right? Network. So this refers to the computers, devices, and resources that are linked together to share information, right? So when we speak about VPN, there should also be a discussion or clarity, or you should have understanding on what cryptography really is. Okay, so this is just an overview. So what are the VPN benefits, right? So a VPN encrypts private data and sends it over a public or shared network such as the internet. The most common and effective VPN technology encrypts traffic flow between specific users, applications, or IP subnets at the network layer or the OSI model. Okay. The VPN is transparent to intermediate network devices and independent of network topology at the network layer. So here, data transmitted over a public or shared infrastructure, such as the internet, is protected by VPNs from threats like man-in-the-middle attacks, right? That's what we spoke about from the previous lesson. Now, by strategically positioning products and capabilities, such as in Cisco, right, we have a lot of these products and capabilities, and you put it throughout the network and utilizing the collaborative capabilities between the platforms, a VPN aims to provide defense in depth, or DID, defense in depth. So VPNs have a number of advantages, right? First is cost saving, as I put here, right? Because VPNs enable organizations to connect remote offices and users to the main corporate site using cost-effective third-party internet transport and avoiding the need for expensive dedicated WAN links. Furthermore, with the advent of low-cost, high-bandwidth technologies, businesses can use VPNs to lower their connectivity costs while increasing remote connection bandwidth. Next benefit is scalability. So VPNs allow businesses to access internet infrastructure to ISPs and devices, making it simple to add new users. And as a result, businesses can add a lot of capacity without putting in a lot of infrastructure. Next is compatibility with broadband technology. So here, VPNs allow mobile workers, telecommuters, and people who want to extend their workday to connect to their corporate networks using high-speed broadband connections like DSL and cable, and giving them greater flexibility and efficiency. In addition, high-speed broadband connections are a cost-effective way to connect distant offices. And the last benefit is security. Of course, right? VPNs can be configured to provide the highest level of security by employing advanced encryption and authentication protocols to keep data safe from unauthorized access. So here, right, this diagram shows where Cisco VPN solutions and Cisco products that supports VPN should be deployed in the network. As you see here, these are the areas where VPN should be used. So we have the campus data center, right? So let's talk about those areas where VPN is actually being used. Okay. First is the enterprise edge network. Okay. So the internet edge, or the enterprise internet edge, which is this one. So the internet edge is the network infrastructure that connects the enterprise to the internet and serves as a gateway to the rest of the cyberspace. The DMZ, right, which is actually in here, right? This is the demilitarized zone. No, actually, this is the firewall, but the DMZ could be in here, right, in between. So the DMZ and the corporate internet access and VPN are examples of internet edge services. Now, remote access VPN services here, right, which is being used by the remote users. These are provided by the internet edge design, allowing mobile users to securely access email, instant messaging, web browsing, and other enterprise-wide services over the internet. Now, if the organization policies require it, remote access VPN also allows mobile users to access the internet and cloud services through a centralized internet connection at the headquarters, which is in here. Right? So imagine this is the headquarters. If they want to go to the internet, they can actually route here, or they have an option to go directly to the internet if they have a direct, if the company allows that. Now, if connectivity over the internet is required, Internet Edge can also provide site-to-site VPN, which is in here, right? To connect remote branches, either to save money on more expensive dedicated WAN links or to provide redundancy for branch offices connected via dedicated WAN links. Now, the Cisco ASA firewalls, right? If you are familiar with this firewalls from Cisco, or the Cisco Firepower next generation firewall, are used to aggregate VPN connections at the internet edge here. Okay, Cisco AnyConnect secure mobility client, right? So AnyConnect, put it here. Is used by mobile clients, the remote users, to provide remote access VPN capabilities for these users. Okay. The next part is the WAN edge. So this is the part of the network infrastructure that connects geographically distant branch offices to a central site or regional hub site. The WAN can be owned by the same company or provided by a service provider, with the latter option being the most common. The WAN's goal is to give branch users access to the same network services as campus users at the central site. The WAN edge design enables secure communication between branches and remote offices over the private WAN. The architecture allows for the deployment of multiple WAN products or WAN clouds for redundancy or load balancing. And additionally, an internet connection can be used as a secondary backup. So here, Cisco firewalls, right, or next-gen firewalls, or Cisco iOS XE routers can be used for VPN connections in the WAN. Yeah, let's also talk about the branch offices here, right, on the right. So this could also be ASA or Firepower, the same thing in this one. So on the branch offices, right, so enterprise branches connect users and devices at a remote location. They usually set up one or more LAN networks and use a private WAN or the internet to connect to the central sites. One or two WAN clouds, as well as a backup internet connection, are accommodated in Cisco branch designs. Direct internet access may be allowed depending on the enterprise access policies, right? So they can do internet or direct internet access. While in other cases, internet access may be limited to a central internet connection at the HQ or the headquarters or regional office. In the latter case, the branch internet connection would most likely be solely for WAN backup. Here, Cisco firewalls, Cisco next-gen firewalls, and also Cisco iOS XE routers can be used for VPN connections from the branch offices going to the HQ or the regional headquarters. All right, let's now talk about the VPN types. So VPNs are classified according to criteria. So based on first, right, based on the deployment mode, where you're gonna have like a site-to-site VPN, right, or a remote access VPN. It could either be based on the OSI layer, right? We have what we call as layer 2 VPN, which refers to legacy protocols such as frame relay, right? L2 MPLS VPN, L3 VPN Internet, or L3 IPsec VPN, and MPLS layer 3 VPN, and layer 7 VPN or SSL VPN. Now, based on the underlying technology, we can have IPsec VPN, an SSL VPN, MPLS VPN, and other layer 2 technologies such as frame relay and hybrid VPNs combining multiple technologies. All right, so if you look at this topology, right, site-to-site VPN, yep, you can use, of course, IPsec in here, right, as well. And here, you have to, for remote access VPN, you can have a VPN client installed on the user site using Cisco AnyConnect. You can also have, or you can also go for a clientless RA VPN using SSL, and you don't need any client here. So you just need to go to the web portal or access the web portal to connect to a specific service in the regional office. Okay. So to keep communication secure, the two basic VPN deployment models are typically used, which is IPsec and SSL. So a site-to-site VPN is a type of one network that connects two locations, right? Site-to-site VPNs link entire networks together. Like, for example, they can link a branch office to the corporate network, right? And in the past, connecting sites required a lease line or frame relay connection. But with the advent of internet access, these connections can now be replaced with site-to-site VPNs. So in the site-to-site VPN, hosts don't use client software. Instead, they send and receive regular TCP/IP traffic, right, as shown here in green, through the VPN gateway, such as, it could be a Cisco iOS XE router, or a Cisco ASA firewall, or Cisco Firepower Next-Gen firewall, as shown in the diagram. The VPN gateway is in charge of encapsulating and encrypting all the outbound traffic, right, which is here, encrypted, right, from a specific site and sending it over to the internet via a VPN tunnel to the peer VPN gateway at the target site, which could be the HQ, right? Because this is where your servers are. So this peer VPN gateway strips the headers and decrypts the content and forwards the packet to the target host within its private network after receiving it. So this is already unencrypted traffic. So companies also use dial-in networks in ISDN before to support remote users in the past, right? So with the introduction of VPNs, a mobile user only requires internet access to communicate with the central office. Telecommuters typically have a broadband connection, such as DSL or cable, to access the internet. Telecommuters, mobile users, and extranet consumer to business traffic can all benefit from RA VPNs or remote access VPNs. Individual hosts who need to securely access their company network over the internet can use RA VPN. So let's talk about clientless SSL VPN, right? Or a VPN client-based RA VPN. So clientless SSL VPN or with a VPN client, such as a Cisco AnyConnect Secure Mobility Client, are commonly used by hosts in a remote access VPN. So Cisco AnyConnect uses a virtual network adapter, right, in the host computer to send traffic back to the VPN gateway in the corporate headquarters, such as a Cisco ASA firewall, right? This could be an ASA firewall, or this is an ASA firewall, or it could be a Cisco Firepower next-gen firewall. Now, users can also use a web browser to create a secure remote access VPN tunnel to the VPN gateway with the clientless SSL VPN, right? Here, there's no need for a client or a software, either software or hardware, actually. From almost any computer that can reach the VPN gateway over HTTPS, clientless SSL VPN provides easy access to a wide range of web resources and both web-enabled and legacy application. Now, currently only Cisco ASA appliances support the clientless SSL VPN. The Cisco Firepower Next-Gen Firewall only supports remote access SSL VPN via the Cisco NConnect Secure Mobility client. Okay, this is short Firepower. Okay, let's now talk about VPN components. So a VPN or a VPN implementation usually includes a number of important components, and any or all of these components will not be included in every VPN implementation. You might not need all of these components depending on your security policies requirements, and you'll need to look at the security policy to see which VPN implementations have the components needed to meet the policy's requirements. So here, the following will be included in the VPN implementation. The first one is authentication. So it's critical to confirm a device's or user's identity, right, before allowing it to connect to your network via VPN. So there's two concepts here. So device authentication and user authentication. Okay, so device authentication allows you to limit VPN access to your network based on authentication data provided by a remote VPN device. Pre-shared keys or digital signature or certificate are the two most common types of authentication. Now, let's talk about user authentication, right? So many VPN implementation will add an extra layer of authentication called the user authentication to check whether a VPN connection is allowed by a user on a specific device. This is commonly used in VPNs for remote access. Now, depending on the VPN implementation, right, or implementation type, the VPN may perform both device and user authentication in some cases. So here, a username and password or a digital certificate are required for user authentication. The password for the former could be a one-time password or a static password through the use of token cards. Now, dual-factor authentication, right? Maybe multi-factor authentication may be required in the most stringent of circumstances. So dual-factor authentication combines something a user knows with something they have, such as static password, and a one-time password generated by a token generator or static password in a tokenless authentication tool like Cisco Duo. Okay, Cisco Duo. Now let's talk about the encapsulation method. So a VPN must also define a encapsulation method, which describes how user information, such as data, is encapsulated and transported across the network. Encapsulation also determines which applications or protocols can be included in the VPN packets payload. Some VPN implementations encapsulate only the application layer data, while others can encapsulate a layer 3 packet or layer 2 frame in its entirety. The next component is data encryption. To prevent eavesdropping, data encryption is used. Data encryption works by running user data and a key value through an encryption algorithm to generate what appears to be a random string of characters. The information can only be decrypted by a device with the same key value. So here you'll encounter this one, right? DES, right? Or the data encryption standard. You also see FIDES or triple data encryption standard. You also see AES, or the Advanced Encryption Standard. We also have Blowfish, RSA, the Reva-Shamir-Adelman algorithm. We also have International Data Encryption Algorithm, or IDEA. And we also have SEAL, or the Software Optimized Encryption Algorithm. Okay. and RC4 are just a few examples of encryption algorithms. Not all VPN implementations, however, support all encryption algorithms. So the next component is packet integrity. So some VPN implementations provide the option of performing packet integrity checking, or also known as packet authentication. Now, a signature, let me put it here, right? Signature is attached to the packet during packet authentication. The signature is created by running the contents of the packet in a shared key through a hashing function, which results in a fixed output known as a digital signature. Okay, digital. This signature is then added to the original packet, which is then sent to the destination as a new altered packet. The sending and receiving systems must first agree on the secret key and the hashing function that will be used to verify the communication's data integrity. Now, the destination verifies the signature before encrypting the packet contents if the signature is valid. Then the output is identical every time, right? The same exact content is passed through the same hashing algorithm. Any small change to the packet content results in a completely different output. If running the content through the hashing algorithms yield the expected result, the packet is considered authentic by the destination. All right, the next component is key management. So here, right, of course, keys are necessary with the VPN connections. And here are a few examples, right? Are they statically or randomly generated? The number of key resets increases security. So there's what we call here, right, as non repudiation as well here. So here it is possible to prove that a given communication took place, right? Non-repudiation is part of a VPN implementation. Non-repudiation in the VPN context means authentication and accounting. Now, to ensure the identity of a device or a user, authentication verifies it. Accounting is the recording of the VPN session. So let me just put here authentication and accounting. Okay. So as I've said, to ensure that the identity of a device or user, authentication verifies it. However, accounting is recording the VPN session. And this can include identifying the two devices that establish the connection and how long the connection was used and how much information was transmitted across it and so on. And this can be used later to detect attacks and to track network usage. Next component is the application and protocol support. Here, selecting a VPN solution requires first deciding which types of traffic require protection. VPN implementations are generally available if you only have IP traffic in your network. And the last important component is address management. Remote access connections address management issues. Assigning an internal address to a remote access client is very difficult. So consider this when choosing a VPN implementation. Some VPN implementations might have bad address management, which could affect your choice in a VPN. So there you go. This is the 1, 2, 3, 4, 5, 6, 7, 8 components that you have to understand in terms of VPN. Okay, now let's talk about cryptographic services. So cryptography, right, is defined as the study of hiding and verifying information. It incorporates protocols, algorithms, and strategies to keep confidential information secure and allow verification of each component in a communication. Through the use of cryptographic systems, confidentiality and integrity can be achieved by utilizing encryption and decryption techniques, hash functions, digital signatures, key management techniques, and various other programs. Security solutions rest on cryptographic tools, while cryptography's primary functions include the following, like confidentiality, right, which gives the assurance that no one can read a particular piece of data except the explicitly intended receivers. Integrity or data authentication. This refers to the assurance that data has not been altered in transit, intentionally or unintentionally. Third is pure authentication. This refers to the assurance that the other entity is who they claim to be. In non-repudiation, right, which is a proof of the integrity and origin of data. The sender cannot repudiate that he or she is the person who sent the data. And the last one is key management, which is the generation, exchange, storage, and safeguarding, use, and vetting and replacement of keys. Cryptographic algorithms can be divided into three categories. So we have symmetric algorithms, asymmetric algorithms, and the hash algorithms. So now let's talk about each of them. So what is symmetric key algorithm? So as shown in the diagram, right, a secret key, okay, or a pre-shared key, first to this one, or pre-shared key cryptography uses a single key for both encryption and decryption. Key lengths in modern symmetric algorithms range from 40 to 256 bits. Now, 3DES or an AES, right, are two examples that has this. And 3DES is a legacy algorithm that consists of 3 consecutive DES encryption decryptions. This designation denotes that 3DES provides a marginal but acceptable level of security, but that its key should be renewed on a regular basis. DES is no longer secure and should be avoided due to its small key size. RC4, right? There's another one here. RC4 should also be avoided. So as a best practice, AES with 128-bit keys provides sufficient security for sensitive data. So to protect classified information of great importance, AES, right, with 256 bits of keys is required. AES is more efficient than 3DES and making it better suited to high throughput, low latency environments, particularly when using pure software encryption. Now let's talk about asymmetric algorithms. Okay. So it is also known as public key cryptography, and it employs a two-key system with one key used for encryption and the other for decryption. Okay. In comparison to symmetric algorithms, asymmetric algorithms are significantly slower. Okay, so take note of this one. So for asymmetric algorithms, the typical key length range is 1 or 1024 to 4096 bits, right? Here we also talk about the DSA, or the digital signature algorithm. We also have RSA, El-Gamal, and the elliptic curve algorithms as examples. The keys are usually referred to as private keys, which is kept private, and the public key, which is made public. Cryptographically, the private and public keys are linked. So the public key cannot be used to generate the private key. Only the key owner can use the private key, while third parties can use the public key to perform operations with the key owner. The Diffie-Hellman algorithm, or the DH, you heard it, is an asymmetric algorithm that negotiates a shared secret key, or a symmetric key, for use by a symmetric algorithm. The Diffie-Hellman algorithm is not directly used for encryption and decryption, but it does allow two parties to generate a shared secret key for confidentiality exchanging information. So the asymmetric algorithms operations are depicted in this diagram, right? So the red key here, right? The red key is assumed to be private, while the blue key is assumed to be public. Okay, and both keys belong to the server on the right side of the figure, right here. So there, the private and public key pair is generated by this guy, right? And the server on the right keeps the private key completely private. This is the private key, completely private, but publishes the public key so that anyone can see it. So this one is being published. The public key was obtained by the workstation on the left from the server on the right, right? And the workstation now encrypts data using the server's public key and sends the encrypted data to the server. With its private key, the server, right, decrypts the data, and only the private key associated with the public key can decrypt data that has been encrypted with the public key, ensuring data confidentiality. All right, so I hope that's clear. That's how asymmetric, that's how the asymmetric algorithm works. Very simple, right? Now, another concept here, which is called the hash algorithm. So their most important property is, irreversibility, as they provide a constant size output for any input. Digital fingerprinting algorithms are also known as hash algorithms. Irreversibility and collision resistance are essential properties for hash functions to be successful. So here you'll hear something like SHA-1 or SHA-2, right? And these are the two examples of hash functions. There's also what we call as MD5 or the message digest 5, which is actually considered an insecure hash functions and should not be used or should be avoided. SHA-1 apparently is an old algorithm that should be also be avoided, and the SHA-2, which includes most widely used SHA-256 and 384 and 512 or 512 functions, right? And it provides adequate security for sensitive data. The hashed message authentication code, right? So HMAC. So when you configure VPN, you're going to encounter all of these terms. So the HMAC is a construction that generates a message MAC using a secret key and hash functions. Integrity verification is performed using HMAC, right? And HMAC MD5 is a legacy algorithm that uses MD5 as its hash function. And again, note that MD5 as a hash function is not really secure. HMAC functions that are more recent, such as HMAC SHA-256, right, should be used or is recommended. Okay, now let's talk about keys. So in cryptography, a key is a piece of data or a parameter that determines a cryptographic algorithm's or cipher's functional output. The algorithm would produce no useful results if it didn't have a key. A key specifies the specific transformation of plain text into ciphertext or vice versa, enduring encryption or decryption. Other cryptographic algorithms that use keys include digital signature schemes and message authentication codes. The majority of attacks on cryptographic systems do not aim to break the algorithm or use brute force key cracking. Instead, attackers will attempt to decipher the complexities of the key management system and practices in which the human factor plays a major role. Now, when dealing with keys in cryptography, these are the considerations to keep in mind. Of course, we have to consider key management, right? Because many cryptographic systems have failed due to mistakes in key management, which is often considered the most difficult and complex part of designing a cryptographic system. For key generation, right, that is the creation of cryptographic keys, either manually or using random number generators. Key verification, key storage, and key exchange, modern cryptographic systems require the services of key management procedures and rely on their strength and reliability. Next is a key generation. So before they can generate a cryptographic key, the peers must first establish trust, right? Now, for the initial IKE peer authentication, IPsec VPNs that use the Internet Key Exchange or IKE protocol for key management may require a PSK or pre-shared key in all VPN devices. The network administrator must generate a key and configure it inside the cryptographic device in this scenario. Although IKE pre-shared keys are used to authenticate peers, They're not used to encrypt traffic between them. Humans are just terrible at coming up with random numbers. So when a system necessitates manual key configuration, it's best to use a good random number generator software and use the results as the cryptographic keys. And the use of good automatic key generation mechanism uh, whenever possible. Okay. Another part is the length of the key or the key length. So asymmetric or asymmetric crypto system security is determined by two factors, right? The algorithm strength and the length of the key. Although the former is more important, the latter, which is the length, is more straightforward to demonstrate. Key lengths in modern symmetric algorithms range from 40 to 256 bits. The key spaces for symmetric algorithms in this range, right, ranges from 240 to 2256. The number of possible key values doubles for every additional bit in the key length. This wide range determines whether or not the algorithm is vulnerable to a brute force attack. Now, if you use a key length of 40 bits, a brute force attack is likely to break your encryption relatively quickly. If your key length is 256 bits, on the other hand, a brute force attack is unlikely to succeed due to the large key space. And of course, right, in for asymmetric algorithms, we're still on the key length, right? The typical key length range from 1024 to 4096 bits. Because the underlying design of the two algorithm families differ greatly, you can directly compare the key length of asymmetric and symmetric algorithms. Right? Now let's talk about key storage. It is critical to keep cryptographic keys safe. Authorized keys can be observed or changed if an attacker has access to the system's storage medium. Always use a key protection method that is appropriate for the sensitivity of the data that these keys protect. The key is generally well protected by encrypted files or even tamper-resistant storage devices. Long-term keys like RSA, right? Long-term key can be stored offline to withstand power outages. So the use of proper methods and guidelines for secure key storage in non-volatile memory can help to eliminate the risk of a key compromise. Now, the last part is key exchange, right? So a key exchange between parties is required in a variety of situations, usually over an untrusted channel. For example, the symmetric nature of HMAC or symmetric encryption algorithms like AES, FreeDES, and so on necessitates the sharing of a secret key by both parties and the use of a secure key exchange method that maintains key confidentiality when transmitted over an untrusted channel. In public key cryptography, subjects' public keys must be made available to other subjects, and the public key's origin or authenticity and integrity must be guaranteed. There's actually a variety of key exchange methods and protocols, and the most common are listed below, which includes the manual key exchange, the Diffie-Hellman algorithm or DH, asymmetric encryption, and the public key infrastructure or PKI. So here, right, the CA signing of user A, right? So here's the CA, the user A, right? So the CA signing of user A identity certificate using CA private key is shown in this diagram. The CA signed user A identity certificate contains the user A public key. The signature of the CA binds the identity certificate, which contains the public key and names of each end user. The certificates are returned to the entity, which installs and uses them until they are revoked or expired. Because each identity now has its own identity certificate, which is signed by the CA and contains its name and public key as well as the CA's public key, each entity can now verify any data assigned by the CA. Now, independent of the CA, the entities can form point-to-point relationship by exchanging information about themselves in the form of verifiable identity certificates. Okay. This capability means that end users can mutually exchange certificates over an untrusted network using the CA's digital signature as the protection mechanisms for the public key exchange after enrolling with the CA and having it sign their public keys. The CA signature is trusted because it can be verified, right? And the CA and its operations are presumably secure. Also, the CA's public key, this guy, right, is also made available in the form of a certificate that the CA issues. Because the signer and the holder are the same person, this certificate is known as a self-signed CA certificate. Now, a document that binds an entity names to its public key is known as an identity certificate. Let me put it here. Identity certificate. The identity certificate is signed by the CA so that it can be verified by all entities. Certificates aren't classified as confidential information, so they don't need to be encrypted. A digital signature, which verifies their authenticity and integrity, is their only defense. So here, this image, right, it shows a digital certificate issued to Cisco.com identity or to Cisco.com. The corresponding public key and CA's digital signature are also shown in this diagram. Now, an X.509 version 3 identity certificate typically contains information such as the certificate holder's name, the public key, and the CA's digital signature. Right? The certificate serial number, the certificate expiration data, the algorithms used to generate the signature, and extensions like certificate revocation list or CRL. Distribution points are among the other fields. So the information contained in the identity certificate is illustrated in this particular table, right? Which contains the following, like the certificate format version, serial number, signature algorithm identified per CA, X.500 name, validity period, subject name, subject public key information, extension, and the serial distribution points and the CA. So the X.509 standard defines basic PKI data formats as a certificate and CRL formats to enable basic interoperability. This format is already widely used in the internet infrastructure in the following places, like secure web servers that use the SSL or TLS protocol for website authentication, for services that use client certificates in the SSL or TLS protocols. Web browsers are required. It can also be on user email agents that support the secure multipurpose internet mail extension or S-MIME protocol for mail encryption. And for IKE RSA-based authentication, certificates can be used as a public key distribution mechanism in IPsec VPNs. Now, when a key is compromised, this can be a problem with PKI. If an RSA private key is compromised, all other entities must be informed that the key and its corresponding public key is no longer trusted. This is known as the certificate revocation. Okay? Now, to address the issue of key compromise, the following certificate revocation solutions are available. So we have CRLs and the OCSP. So let's talk about each of them, right? So using a CRL, which contains a list of all certificates that are no longer valid, a PKI can provide a simple solution that is revoked. The CRL is timestamped with defined lifetime and signed by the CA. It's kept on an HTTP server or an LDAP directory, a web server that supports SCEP or Simple Certificate Enrollment Protocol or somewhere else. After the old CRL expires, the PKI end user is responsible for obtaining a new one and comparing any certificate it wants to use against the current CRL. So the main weakness of CRL is that they may contain stale information because they're issued on a regular basis, usually every couple of hours. If a key is compromised in the middle of that period and a new CRL is issued soon after, there is a vulnerability window during which the attacker can use the compromised key while endpoints continue to use the old CRL till it expires, which does not contain the compromised key. So here, right, OSCP, this guy, is a protocol for checking certificates against a database of revoked certificates in real time. The end user or device requires or queries the OCSP server after receiving the certificate of another user to ensure that the certificate has not been revoked, right? OCSP overcomes the shortcomings of CRLs, but it necessitates a highly available OCSP server infrastructure. By the way, OCSP means Online Certificate Status Protocol. Okay? So that's the end of the lesson. So here we discuss about basic cryptographic components and principles. And we also cover the following, like VPN types, the VPN components, cryptographic services, keys, and public key infrastructure, or PKI. Thank you very much for watching the video. Hi, welcome to our Cisco CCNP S-Core video course. On this lesson, we're going to talk about site-to-site VPN topologies and remote access VPN. So, a VPN that uses IPsec transmission protection technology and is deployed on a shared infrastructure is known as IPsec VPN, right? IPsec VPN. So, a site-to-site IPsec VPN can be used to replace or supplement existing private networks that connect enterprise sites as an alternative to a WAN infrastructure. IPsec VPNs do not change WAN requirements such as high reliability and extensive scalability inherently, right? And rather, they meet these requirements more cost effectively and with greater flexibility. IPsec VPNs can use a variety of topologies and technologies, so you could be familiar with them before designing a site-to-site VPN solution. So the interconnection of network nodes into a network is referred to as a network topology. Because the physical interconnection of networks devices has no bearing on how VPN protocols create connectivity between network users, most VPN technologies rely on logical interconnection. The following are the three most common logical VPN topologies used in site-to-site VPN. The first is individual point-to-point tunnels, or individual point-to-point VPN connection. It is a secure VPN path that connects two sites. Individual point-to-point VPN connections that connect sites that require mutual connectivity may be present in the network. Next is hub and spoke. A hub and spoke network is one in which one central site, right here, serves as a hub with all other sites which we call as the spokes, right? And they have peering and exclusively with the central site devices. Although the hub may be able to act as a relay and facilitate spoke-to-spoke communications over the hub, most user traffic flows between the spoke network and the hub network. The third one is a full meshed network, right? Shown here. So here, every network device is connected to every other network device in a fully meshed network. This topology enables any-to-any communication and provides the network's most optimal direct paths and gives network users the most flexibility. There's also some additional complex topologies that can be created in addition to these three main VPN topologies. So this could be partial mesh. We also have a tiered hub and spoke topology, right? And a joined hub and spoke topology. All right. So as part of the, exploration on this VPN topologies, I would appreciate if you could also do some research on what's the difference between this and what are the advantages of this one and to the main categories of the site-to-site VPN. Okay. So site-to-site VPNs, right, are used to connect geographically dispersed site of the same company or to connect to partners over a public network as a replacement for a traditional routed WAN. This type of connection saves money while also allowing for scalability. Site-to-site VPNs authenticate VPN peers and network devices to provide VPN functionality for an entire site while also providing transmission security between sites over an untrusted network like the internet or an MPLS WAN. So VPN devices use basic firewall-like controls to limit connectivity and prevents traffic spoofing when traffic flows over site-to-site VPNs. These VPN networks frequently operate over more tightly controlled transport networks such as MPLS and rarely encounter traffic filtering issues between VPN endpoints. Because these VPN networks provide core connectivity in an enterprise network, they are frequently required to provide high availability and high performance services to critical enterprise applications. So side-to-side VPNs, right, have the following properties. Of course, right, it connects sites as a replacement for a classic one. It uses peer or site authentication and cryptographic protection. It requires basic network traffic controls. It uses IPsec for its cryptographic security services. It works over controlled networks like MPLS or internet transfer networks. It often requires high availability and performance guarantees like in QoS, right? And it can be configured in several different ways on the different services. Site-to-site IPsec technology is used by VPNs to encrypt traffic transmitted over public networks. While IPsec provides a standard method for transmission, security, and key management, it comes with a variety of deployment options and does not provide all scalability mechanisms for large network on its own. As a result, a thorough examination of the network environment and requirements is required before selecting the best site-to-site IPsec VPN implementation option. There's actually a variety of site-to-site VPN implementations available, and each of which allows the site-to-site VPN to function in unique ways. First is the DMVPN. So the DMVPN solution, or the Dynamic Multi-Point Virtual Private Network Solution, for example, allows for on-demand full mesh connectivity with simple hub-and-spoke configuration and zero-touch deployment for adding remote sites. Next is Cisco Flex VPN. It makes use of the capabilities of Internet Key Exchange version 2 or IKV2 to combine various VPN types and topologies under a single configuration language. Site-to-site IPsec VPNs are supported by the Cisco Adaptive Security Appliance or ASA firewalls and Cisco FarPower Next-Gen firewalls and Cisco iOS XE routers, right? Also, DMVPN and FlexVPN, for example, are only available on Cisco routers, however, not available in firewalls. IPsec provides several encapsulation protocols, for example, authentication header and ESP, or encapsulating security payload, and more importantly, encapsulation modes to encapsulate user traffic, transport mode, tunnel mode, and mixed mode that is used by the group encrypted transport VPN or get VPN. While most site-to-site VPNs use IPsec tunnel mode or for transport, right? Some technologies such as get VPN use a mixed encapsulation mode, which can be considered non-tunneling and poses challenges over public networks. So there are three major implementation aspects of site-to-site IPsec VPNs, which includes the following. First is the IPsec transport mode, right? Here, the original IP header is preserved and no additional IP headers are added. Thus, routing is done using the true destination and source IP address. Next is the IPsec tunnel mode. Here, the original IP header or the inner header is preserved and a new outer IP header is used to identify the tunnel endpoints. Thus, routing is done on the new outer header, which is the IPsec tunnel's destination and source. And the third one is get VPN. Like in IPsec tunnel mode, get VPN mixes this by adding a new outer IP header, but the new outer IP header is a copy of the original IP header. So it's like tunnel mode, but with the identical inner and outer headers. So some of the additional characteristics of this implementations, right, is scalability of configuration. As the number of peers in a VPN grows, the effort required to add or move sites from the VPN becomes unacceptably complex. As a result, a network designer must choose between non-scalable manual VPN peering provisioning methods and configuration scalability methods that reduce the amount of effort required to manage VPN peerings. There's also another key consideration here, which is about peer scalability. So here we're talking about pure authentication in IPsec VPNs. Like configuration scalability can become a complicated issue as the size of the VPN grows, especially in large partially meshed and fully meshed VPNs. In these VPNs, each peer may be required to authenticate a large number of other peers and necessitating the provisioning of scalable authentication credentials in the network. So here, pre-shared keys or PSKs that are shared between pairs of peers do not scale well because in a fully meshed network, you would need to provision an n times n minus 1 over 2 of such password, right? Because it's mesh. So the use of certificates to facilitate PKI, facilitated authentication, is a scalable solution, but it requires an organization to properly maintain a PKI and its supporting infrastructure. Now, based on the previous implementation aspects, right, and required topology and available devices, you can choose from the following VPN technologies and implementations that are available on Cisco devices. So as you will see here, we have static crypto maps, static VTI, DMVPN, and Flex VPN, and the Get VPN. And on the left side, right, it's going to give you the criteria, right, like the encapsulation, configuration scalability, authentication scalability, suitable topology, suitable transfer networks, and availability. And inside it, right, you can see the characteristics of each of the settings, right, based on the criteria, right? So this is a very good reference if you are deciding on which type of VPN implementation do you want to use, okay? So going in detail, right, of each of the implementation. Let's talk about the first one, which is IPsec static crypto maps. The cryptomap-based configuration approach on Cisco devices is a legacy method of configuring site-to-site VPN. This method employs policy-based configuration in which only a subset of traffic on a given interface is encrypted and encapsulated according to a set of rules. When you use a cryptomap approach, you create a cryptomap object, right? Here. So within that object, you specify the IP address of the VPN peer, the set of cryptographic algorithms that will protect traffic, and the ACL or the access list that defines a subset of traffic that needs to be encrypted. Cryptomap is then applied to that interface, right? This legacy approach is still used in many IPsec VPN implementations. Because of its ubiquity, it is well known to network administrator and is interoperable with many vendors. So crypto maps have the following benefits when compared to other configuration approaches, right? So it is well known in terms of configuration. It has interoperability with other vendors and the cryptographic protection built into the concept of crypto maps. In terms of limitation, there's no support for multicast. There's no support for routing protocols over the VPN tunnel. It is complex and non-intuitive configuration, and it has limited interoperability with other Cisco iOS and iOS XE software features. So here, crypto maps are supported on Cisco iOS and Cisco iOS XE, software routers, Cisco ASA appliances, and Cisco Farpower next-gen firewall devices. Next is IPsec static VTI. Okay, so when providing protection for site-to-site VPN tunnels, the use of IPsec VTIs, right, simplifies the configuration process and provides a simpler alternative to using GRE tunnels or crypto maps with IPsec. One of the biggest advantage of IPsec VTIs is that they don't require a static mapping of IPsec sessions to physical interfaces. So here, a virtual interface is associated with the IPsec tunnel endpoint. Because the tunnel endpoint is a routable virtual interface, many common interface capabilities can be applied to the IPsec tunnel. VTIs use a route-based approach to configure IPsec VPNs, encrypting and encapsulating all traffic entering the virtual interface. Routing is in charge of directing traffic to the virtual interface. Now, when you use the VTI approach, right, you create a virtual tunnel interface and use tunnel protection to apply an IPsec profile to it. Because crypto maps are automatically generated for each tunnel, it requires fewer configuration lines. Plain text packet features are configured on the VTI, while encrypted packet features are applied on the physical interface. So static VTIs, right, provides a routable interface type for terminating IPsec tunnels, as well as a simple way to define protection between site and an overlay network. A VTI allows interface commands to be applied directly to IPsec tunnels and support native IPsec tunneling. a virtual interface is associated with the IPsec tunnel endpoint because the tunnel endpoint is a routable interface. Many common interface capabilities can also be applied to the IPsec tunnel. Interoperability with other vendor standards-based IPsec installations is supported by VTIs. SVTIs have a number of characteristics, which includes the following. They function as regular tunnels, right? One for each VPN remote site. The tunnel protection concept is used to apply cryptographic protection to traffic and is not part of the tunnel interface itself. IPsec ESP or AH is used to encapsulate them, and the state of the VPN tunnel determines their line protocol. Now, when compared to a cryptomap-based configuration approach, an IPsec SVTI or static VTI has several advantages. First is simplified configuration, right? Because when compared to cryptomaps or GRE IPsec tunnels, you can use virtual tunnel constructs to configure IPsec peering and reducing the complexity of the VPN configuration. It provides flexible interface feature support. Good that it supports multicast. It has improved scalability, and it provides a routable interface. VTI IPsec is supported on Cisco iOS and Cisco iOS XE software routers and Cisco ASA with software version 9.7.1 and above appliances. Let's talk about the third one, which is DMVPN. DMVPN is a Cisco iOS software solution that allows you to create scalable IPsec VPN tunnels. Cisco VPN uses a centralized architecture to make deployments with granular access controls for a variety of user communities, such as mobile workers, telecommuters, and extranet users, and it's easier to implement and manage. Cisco DMVPN enables branch offices, right, which is in here, to communicate directly with each other, right, this one, over a public WAN or the internet, such as when using VoIP between two branch offices without the need for a permanent VPN connection. It enables zero-touch IPsec VPN deployment and improves network performance by reducing latency and jitter and optimizes head office bandwidth utilization. So to combine the best of hub and spoke and fully meshed topologies as well as provide some other features, DMVPNs employ the following mechanism. First is what we call as MGRE, or the multi-point GRE. This technology allows a single GRE interface to support multiple GRE tunnels and reducing the configuration complexity. IP multicast and non-IP protocols are also supported by GRE tunnels. As a result of IP multicast, the designer can use routing protocols to distribute routing information and detect VPN changes. To build tunnels between devices, all DMVPN members should use GRE or MGRE interfaces. Next mechanism is what we call as the NHRP, or Next Hop Resolution Protocol. NHRP is a client-server protocol in which the hub serves as an NHRP server and the spokes serve as NHRP clients. Each spoke's outer and tunnel IP addresses are stored in an NHRP database maintained by the hub, right here. When a spoke boots, it registers its public and internal tunnel addresses. And when building direct spoke-to-spoke tunnels, it queries the NHRP database for the addresses of other spokes. The NHRP protocol is used to reduce the configuration complexity of fully or partially meshed VPNs to a level comparable to hub-and-spoke VPNs. IPsec provides GRE tunnels with transmission security. DMVPNs create a permanent IPsec hub-and-spoke VPN that can dynamically reconfigure into a partial or full mesh as needed. Right? That's IPsec. Third mechanism. So to discuss about the advantages, here are the advantages or primary advantages of DMVPN. So hub router configuration reduction, right? So traditionally the cryptomaps characteristics, the ACL and the GRE tunnel interface for each spoke router are defined on the hub router. Here, users can configure a single MGRE tunnel interface in a single IPsec profile using the DMVPN feature, which eliminates the need for crypto ACLs on the hub router to manage all spoke routers. As a result, even if spoke routers are added to the network, the size of the configuration on the hub router remains constant. Next is automatic IPsec initiation. So here, GRE uses NHRP to configure and resolve the peer destination address for automatic IPsec initiation. As a result, without any IPsec peering configuration, this feature allows IPsec to be immediately triggered to create point-to-point GRE tunnels between spokes. And third is the support for dynamically addressed spoke routers. So when configuring a hub router for a point-to-point GRE and IPsec hub and spoke VPN network, you must know that the physical interface IP address of the spoke routers, because this is the GRE and IPsec tunnel destination address. DMVPN allows spoke routers to have a dynamic physical interface IP addresses, and NHRP, or Next Hop Routing Protocol, right, is used to register the spoke router's dynamic physical interface IP address with the hub router. Some additional concepts about DMVPN. DMVPN supports two deployment models as shown in this figure. First is a hub and spoke, right? And the other one is hub and spoke and spoke to spoke. So hub and spoke, or a spoke to spoke deployment model, can be supported by a DMVPN cloud topology. Each hub router has a mGRE interface, and each branch router has a point-to-point GRE interface in a hub and spoke deployment model. Both the hub router and the branch router use mGRE interfaces to forward traffic to other peers in a spoke-to-spoke deployment, right here. When traffic needs to be sent from one spoke to another, IPsec tunnels between the spokes are automatically established and do not require any additional configuration on the spokes, right here. A DMVPN cloud is a collection of routers that share the same subnet and are configured with either an mGRE interface or a point-to-point GRE interface, or a combination of the two. Here, Cisco IOS and Cisco IOS XE software routers support DMVPN. All right, let's now talk about remote access VPNs. So the client-based secure sockets layer VPN, or SSL VPN, remote access using Cisco AnyConnect Secure Mobility Client and VPN headend, right, which is implemented on the Cisco Adaptive Security Appliance, or ASA, and Cisco NextGen Firewall, is the most popular method for deploying a remote access VPN. So to establish an SSL tunnel with a VPN headend, the most basic Cisco AnyConnect client-based VPN solution uses the Cisco AnyConnect Mobility Client version. Bidirectional authentication is used in the basic solution. This means that the VPN client authenticates the VPN headend using a certificate-based authentication method, and the VPN headend authenticates the user using a username and password against its local user database. Now, the VPN headend applies a set of authorization and accounting rules to the user session after authentication. The remote user can forward raw IP traffic into the SSL tunnel once the VPN headend has established an acceptable VPN environment with the remote user. To provide this functionality, the Cisco AnyConnect client creates a virtual network interface, and this virtual adapter requires an IP address. The most straightforward way to do so is to create a local pool of IP address on the VPN headend. The client can use any application to access any resource behind the VPN gateway, subject to the VPN session's access rules and split tunneling policy. Let's talk about our VPN configuration concepts. VPNs connect different types of remote users or sites, right, to secure network or over an insecure transport network. These users or sites security policies may be complicated, and there may be several different user groups, and each with their own set of environments. Now, to make provisioning of such a configuration manageable, VPNs require a flexible and scalable configuration method. Here, you should be able to apply network settings and security rules to any specific user group, or site using the configuration method. Furthermore, the configuration method should allow you to create small exceptions to group security policies or configure similar policies for different groups with little effort and no duplication of workload. These capabilities should be provided by mechanisms that provide appropriate configuration modularity and inheritance in a configuration hierarchy. Now, when configuring the VPN policy, the Cisco ASA appliance and Cisco Firepower Next Gen Firewall use a separation of access methods and policies to provide flexibility and scalability. There are actually two main configuration constructs that you have to be aware of, right? First is the connection profile and the group policy. So in connection profiles, right, for a specific access method, connection profiles define the authentication parameters and protocol-specific parameters like the pre-login requirements. For the group policy, reusable group policies are a set of user-oriented attribute value pairs that define the terms of a connection after it has been established. In other words, after a user authentication, right, group policies define the post-login settings and security policies that must be applied to a remote session. If you look at this figure, right, it shows you an example of modularity and inheritance of group policy. This one, right, the DFLT group policy is the default group policy for each system. All other policies inherit the default group policies, non-explicitly defined values. This allows all users and user groups to share common settings within a single configuration object. The employee policy, right, for example, specifies some employee specific settings and inherits all non-defined settings from the default group policy. If specific settings are required for specific users, such as IT or the engineer's policy right here, you can create additional group policies that can only contain those settings and inherit the rest of the parent policy. Several resources can be used to obtain user-oriented attributes for a remote access VPN session. Also, individual attributes can be set in a user profile in the Cisco ASA local user database when using the Cisco ASA appliance as a VPN headend. The connection profile, right, can be given a group policy. This method is useful when you need to apply the same policy to all users connecting to the VPN. So if you use attributes from a variety of sources, they are assigned in the following order, right? So first, you should have the user attributes retrieved from the local user database or AAA server. Then this attributes assigned through a group policy attached to the local user account or pushed from the AAA server. Then you're going to have attributes that are assigned to a connection profile through a group policy, and the default group policy has attributes assigned to it. That's the end of the lesson. In this lesson, we covered the different site-to-site VPN topologies and flavors, and we also spoke about remote access VPN. Thank you very much for watching the video. Hi, welcome to our Cisco CCNP S-Core video course. On this lesson, we're going to explore the following topics covering security, intelligence, and endpoint protection. So as modern networks use a wide range of applications, right? Protocols and ports and different types of network attacks are increasing and evolving on a daily basis. Different types of network security technologies has been developed to mitigate or defend against these attacks. Email content security systems, for example, defend against email-based attacks, while web content security systems defend against web-based attacks. Similarly, different types of security appliances are designed to fulfill various mitigation functions. Now, implementing basic firewall technologies has been the traditional approach, right, to network defense. As attacks target legitimate systems and software applications that are permitted to traverse the networks and firewalls, this approach is no longer an effective or fail-safe mechanism. To combat today's advanced threats and attacks, the enterprise needs defense in-depth strategies and security solutions that work across the attack continuum. So security has progressed from traditional perimeter defenses, right, to a comprehensive, all-encompassing and actionable model. Modern security solutions must be capable of securing any device across any network and to any applications, and must address network security challenges from the attack continuum perspective. The attacks are divided into three phases, right? First is the before, then the during, than after the attack. This continuous model is consistent with how companies secure, defend, and audit networks on a day-to-day basis, and can help analysts suggest better solutions that provide protection throughout the attack continuum. Looking at the attack continuum while attempting to defend the network is the best way to communicate the full scope of the security challenge. The purpose of using this security model is to emphasize that there's no such thing as a silver bullet. So, security methods, right, must not only focus on detection, they must also be able to mitigate the impact once the attacker has gained access. Organizations must examine their security model holistically in order to gain visibility and control across the extended network and the entire attack continuum. The before, during, and after an attack has begun to damage systems or steal information. Today's network security controls should be able to protect against all types of attacks. And as shown here in the diagram, right, using a threat-centric security model addresses the entire attack continuum across all attack vectors. So again, right, the three phases of the attack are as follows. The first is the before. Here. So before you begin, you must first understand what you're defending. To defend your network, you'll need a device inventory like the devices, operating systems, services, applications, users, and so on. Implementing access controls, enforcing policy, and blocking applications, and overall access to assets will reduce the scope of the network's attackable surface space, wasting time and money. Unfortunately, even with the good access controls, attackers have a relatively easy time breaching the network perimeter. Firewalls, next-generation firewalls, NAC or Network Admission Control, and identity services provide security professionals with the tools they need to detect threats and enforce and harden policies prior to an attack. Next is the during, right? So if an attack succeeds, you must be able to detect it. You must use the most advanced threat detection systems available. When an attack is detected, you can defend the environment by blocking it. NGIPS, email security, and web security solutions all assist in detecting, blocking, and defending against attacks that have penetrated the network and are in progress during an attack. Third one is after, right? So attacks will almost always succeed, and you'll need to determine the extent of the damage, contain the event, and remediate and restore normal operations. You must also address a wide range of attack vectors with solutions that work anywhere a threat may appear. So here, advanced malware protection, right? You can also use SIEM, right? Or security information and event management, and network behavior analysis after an attack to quickly and effectively scope, contain, and remediate an attack to minimize the damage. Organizations can also use solutions like advanced malware sandboxing. So here, organizations need solutions that span the entire attack continuum and are built on the tenets of being visibility-driven, threat-focused, and platform-based to overcome today's security challenges and gain better protection. Cisco, for example, has a broad range of security solutions that cover the entire attack lifecycle. Now let's talk about security intelligence, right? So here, security intelligence is, or threat intelligence or cyber threat intelligence or intel for short, is a critical tool that in the fight against cybercrime. Threat intelligence, well, according to Gartner, is evidence-based knowledge, including context, mechanisms, indicators, implications, and actionable advice about an existing or emerging threat or hazard to assets that can be used to inform decisions about subjects' response to the threat or hazard. So one of the first lines of defense against cyber attacks is good security intelligence. So here you can use security intelligence feeds, right, for example, and can be used to block connections immediately based on the most recent reputation intelligence, obviating the need for a more resource-intensive and in-depth packet analysis. So the Cisco Talos Intelligence Group for example, is a market leader in threat intelligence. The Talos Intelligence Group is made up of top threat researchers who create threat intelligence for Cisco products in order to protect customers from both known and unknown threats. The result is a security intelligence cloud that generates big intelligence and reputation analysis by tracking threats across networks, endpoints, mobile devices, virtual systems, the web, and email, resulting in a comprehensive understanding of threats, their root causes, and outbreak scopes. Security intelligence can be used to drop specific malicious traffic before it is further analyzed by the access control rule, right? As shown in the figure, where we have a Cisco Firepower Management GUI, right? Here. So we have visibility on the access control policy rule configuration. So here's also a partial screenshot of the Cisco Firepower Management Center GUI here. So the security intelligence feed monitors known attackers, bogus IP addresses, and other threats before categorizing them. The blocked IP address are classified as malware and attackers by the security intelligence. As shown in the figure, right? Clicking any of the categories will display details of each block connection, right? Including its source IP address, destination IP, and type of threat, and so on. Now, when connections were initiated from internal network IP addresses to the block IP address in the previous figure, without requiring a deeper analysis of the packet, the security intelligence feature immediately blocks the connection. It also classifies the connection of the IP address, right? Here, as malware. This event notifies which host in your internal network may have been infected with malware. So this is the internal network, allowing you to conduct further investigation into host software, operating system, and patching status, among other things. Overall, the data generated by Cisco Firepower Management Center is useful in narrowing down the threat and taking protective measures. Now let's talk about endpoint protection. So securing your endpoint differs significantly from securing your network, right? You can use your network to protect your endpoints in legacy network architecture because you cannot guarantee that your endpoints will always be behind your network. And this strategy is less useful in modern mobile and cloud-based environments. As your company endpoints connect to business partner networks, hosted environments, and other networks that you don't control, you must prioritize endpoint security over network security. Both are critical issues that must be addressed though. Now, by providing visibility and clarity to previously unknown artifacts in Exchange files and by seeing a threat once and blocking it everywhere, Cisco Advanced Malware Protection, or AMP, speeds up the security response. Cisco AMP is available on both network devices and endpoints, addressing network and endpoint security. The AMP solution is positioned as an endpoint protection platform, or EPP, in the context of AMP for endpoints, which provides many capabilities to protect endpoints. So here, Cisco AMP for endpoints is just one of the several components in the AMP architecture. The integration of different components, right, such as Cisco Firepower, Next Generation Firewall, Cisco ESA, or Email Security Appliance, Cisco WSA. Talos Threat Intelligence powers the AMP Cloud, which is where malware is detected. Any AMP architecture component can send a file to the AMP Cloud for analysis. If a file is unknown to the AMP Cloud, it can be sent to the Threat Grid Cloud sandbox for further analysis. Users can also manually submit files to Threat Grid. Here, right? Cisco AMP Cloud notifies all AMP components around the world when Threat Grid issues a conviction. The components of the AMP for endpoints solution are depicted in this diagram, right? The following are the components of the solution. First is the AMP Cloud. So the virus detection and analytics engine are housed in the AMP Cloud. Next is the AMP Threat Grid. This product is cloud-based unboxing solution that thoroughly examines files, samples submitted to the AMP Threat Grid Cloud. The analysis results are fed into the AMP Cloud, where they can be used to update file disposition based on the findings. Now, there's also what we call as AMP connector, right? AMP connector, which is a component that runs on endpoints. It communicates with the cloud to send and receive information about files and their disposition. There's actually several connector options available. First is the AMP Windows connector, right? Which you can use this connector to communicate with the AMP cloud for file disposition checks, system command and control functions, and software updates on a Windows-based hosts. Apple devices running OS X 10.7 or later are supported by the AMP macOS connector. If you choose this connector as an installation option in the Mac policy, it has a limited graphical interface that you can access from the menu bar. ClamAV is used as the offline detection engine in the Mac connector rather than Tetra, which is used in the Windows connector. Next one is the AMP Linux connector. It works with Red Hat 6.5 and 6.6, as well as CentOS 6.4, 5, and 6. ClamAV is used as the offline detection engine in Linux connector rather than Tetra, which is used in the Windows connector. Fourth is the AMP for Android, or the AMP Android connector. This application can be installed on an Android device to communicate with the AMP cloud for mobile malware detection. Only the Android operating system is currently supported. Next is Clarity for iOS. This application can be installed on an Apple iOS device to communicate with the AMP cloud for mobile malware detection. It also includes Cisco Umbrella integration. And the last part is the AMP console, right? This is the web-based GUI that allows you to manage all your endpoints. For the AMP console, there's actually two options. If you use private cloud, the console is hosted on an AMP private cloud appliance in your internal network. The appliance acts as a proxy to the AMP cloud or as a local copy of the AMP cloud in your network. So that's private cloud option, right? Private. And you also have the public cloud option. So if you're using a public cloud, Cisco will host the console on the internet for you. Okay. The most common AMP for endpoints deployment type is to use public cloud. The private cloud option will not be discussed further though, right? So the operations for AMP for endpoints are summarized below. So when a file is moved, executed, or copied, the AMP connector calculates its hash, right? And queries the AMP cloud for file verdict. At this point, only the hash of the file is sent to the cloud. The verdict can be clean or contain malware for files that are already known to the cloud. The returned verdict is unknown if the file is unknown to the cloud. Now, the AMP connector can be configured to send the entire file for sandbox analysis if the verdict is unknown. Dynamic analysis is the term for this procedure. The file is uploaded to the AMP cloud and analyzed in the threat grid cloud, which is in here, right? Or analyzing the threat grid cloud sandbox. Users can also manually submit files to threat grid, either through the AMP or the threat grid console. Threat grid updates the verdict in the AMP cloud when it uses a conviction. The AMP cloud then uses the retrospective event to notify all components that have previously seen the file about the decision. Now let's talk about the Cisco AMP for endpoint use cases, right here. Cisco AMP for endpoint, right, is a public cloud-based service that only requires the endpoint connector to be installed. And if you're using the public AMP cloud, the rest of the configuration is done in the publicly accessible AMP cloud or console. The diagram shows where Cisco AMP for endpoint components should be installed in the network. The AMP connector must be installed on endpoints. The connector communicates with the AMP cloud to send and receive information about files and their disposition. The AMP cloud is the hub of intelligence for all AMP technologies. There are currently 3 AMP clouds, one in the US, one in Europe, right? And one in the Asia Pacific region, Japan and China. There is a public cloud option as well as a private cloud option. The intelligence will always come from the AMP cloud, regardless of which option you choose. Okay? So that's the end of the lesson. Here we covered security intelligence and endpoint protection using AMP. Thank you very much for watching the video. Hi, welcome to our Cisco CCNA Security video course. On this lesson, we're going to explore SDN Concepts, network programmability and automation, Cisco platforms and APIs, and Python scripts for automation. So broad industrial trends have inspired more particular networking trends, right? And which are changing how network engineers design and maintain new infrastructures. It has necessitated the development of new skills required to create and manage networks and prompting Cisco to incorporate programmability features into its platforms. In this lesson, you'll master the fundamentals of software-defined networking, or SDN, right? Which is intended to make a network more flexible and agile, allowing you to install, administer, and program networks more quickly. You'll also learn about network programmability and automation, as well as the supported application programming interfaces, or APIs, on various Cisco platforms. So SDN is defined or was created in response to the growing requirement to automate, scale, and optimize networking so that application diversity and agility can be facilitated. SDN separates the control and forwarding planes, allowing you to design, create, and manage networks. As a result, the control plane may be directly programmed and hides the underlying infrastructure from applications and network services. SDN is defined as follows, right? So control and data planes are disconnected, right? So take note of that. And intelligence and state are logically centralized in this networking method and architecture. The core network infrastructure is separated from the applications, or which we call as network virtualization. And external systems can influence network provisioning, control, and operations through the use of programmatic interfaces. Now, SDN, on the other hand, is not an all-in-one solution for all networking issues, right? So remember that. It's not developed to take the place of network engineers. All network engineers must become programmers, right? As a condition of employment. So it's not like that. And it's not about attempting to evolve a network in a new way. Okay? Let's have a quick comparison between traditional and SDN, right? Or traditional networking and SDN. So in traditional networks, the control plane of network devices, right, processes traffic that is critical to maintaining the network infrastructure's functionality. It is made up of apps and protocols that are used to learn and calculate forwarding decisions between network devices. Now, data packet flow is managed by the data plane, which is shown here as DP. While traffic is being forwarded through the network device, it acts on the forwarding decisions. So on this figure, right, it shows an example of a traditional network. So each device in the architecture has a control plane, or CP, and a data plane, or DP. Since the control plane exists, all devices are equally intelligent and capable of making decisions on their own. Now, the data plane, of course, is in charge of actual packet routing. It can be partly or entirely hardware-based with ASICs frequently used, and is hence extremely fast. Despite the fact that this sort of network is now known as traditional network, it's still the most widely used. Now, when SDN was introduced, it was first considered that the control plane should be removed from each device and centralized into an SDN controller. The strong separation of the control plane and the data plane is a classic SDN notion, right? This one. So as indicated in this diagram, the controller controls all of the decisions regarding how network devices operate, while the network device is deemed dumped, that it lacks intrinsic control capability, right? As this is being controlled here. This method allows you to evolve control plane protocols independently of hardware while maintaining a centralized control that can manage many data plane elements. Still, in the conventional SDN architecture, the total separation of the entire control plane from the data plane is a dramatic change from how most networks are designed and operated today. Aside from the advantages, this technique poses possible issues in terms of scalability, availability, and performance. The controller must be able to scale to very large networks with thousands of nodes, as well as be highly available and perform well or enough to handle the network quick requests and intense load situations. Now, another option is what we call as a hybrid SDN, okay, which combines the best of both worlds by allowing traditional networking and SDN to coexist in the same environment. As seen in this illustration, right, this can be performed without completely disconnecting the control and data planes. So the hybrid SDN strategy can take advantage of both hardware intelligence, right, and the conventional network operating system feature sets. Traditional routing protocols that work and scale effectively, such as BGP, right, which makes the internet work today, can still be used. You can also utilize a centralized controller here, right, that provides a single window for API management. A single API would serve as the network interface rather than individual control of each network device to make changes or retrieve data. This method allows you to pick and select which programs and functionalities should be moved from the network device to the controller. So here, SDN provides a centralized programmable network made up of the following components. First is the SDN controller, which is this one, and the northbound APIs and the southbound APIs. The SDN building blocks and their interactions with applications and services, as well as networking devices, are depicted on this diagram. So first, the controller, right here. So in a broad sense, it's a collection of software that replaces or extends the control operations that were formerly part of the embedded operating system in network device. SDN controllers are the network's brains, providing a centralized view of the entire network. Rather than being a mechanism to customize network control plane behavior in devices, the controller is an active member of the distributed network control plane. Now let's talk about the northbound APIs. These are APIs, right? Or APIs to communicate with applications and services running on the network. So the controller, for example, supports northbound representational state transfer or REST APIs, which allows applications to connect to the network. REST is an architectural style for distributed hypermedia system that abstracts architectural aspects. REST focuses on the functions of components, the limits on their interaction with other components, and their interaction of relevant data pieces, rather than the intricacies of component implementation and protocol syntax. As a result, REST APIs, which are based on HTTP, right? So let me write it here. REST based on HTTP and JSON are becoming increasingly popular as programming infrastructure. Now, the other one is southbound APIs, right? So southbound APIs send the data to the network switches and routers. As a result, the controller makes use of these APIs to make dynamic adjustments in response to real-time requirements, as well as receive information on the state of devices. These APIs support heterogeneous network environments by connecting to virtual and physical network elements. So here, right, well, one example is OpenFlow, for example, is a southbound interface. Let me put it here, OpenFlow. So it's a southbound interface designed by the Open Networking Foundation, or ONF, that allows the SDN controller to alter the forwarding plane of network devices in order to react to changing business requirements. So more particular networking trends have been driven by broad industry trends, which are defining IT and making it more responsive to changing business and application needs, and boosting agility and adding business value. Now, the following are some specific networking industry trends. First is open source software here. It's actually a community-driven methodology for developing and maintaining software that increases flexibility and customizability while minimizing the required capital investment. As a result, open source software development can keep up with many commercial products. Next is programmable infrastructure. It's a key concept to grasp, right? Where or a key concept to grasp is the network programmability, which aims to significantly reduce human-machine interaction in order to achieve the goals of SDN in the DevOps movement. And as a result, network programmability is a very real feature of SDN in use today. Third is SDN. So SDN means software-defined networking, right? And it refers to a set of approaches for managing and changing a network behavior through an open interface rather than a closed box method. Disaggregation of a network devices control and data planes, virtualization of network operations, policy-centric networking, and a shift towards open protocols are all prevalent features in this trend. Fourth one is DevOps. DevOps is a cultural trend that aims to develop and promote ways that increase the speed and agility of a system and infrastructure deployment, maintenance, and improvement. It's critical to recognize that this cultural shift is forcing network engineers to use better configuration and automation technologies. And the last one is application-centric infrastructure. Application-centric infrastructure is becoming more popular in the networking business. It's pushing a policy-based networking paradigm like Cisco's ACI infrastructure, right, or application-centric infrastructure, which automates and accelerates data center application deployment. Open source software, right, as I've said earlier, is part of a community-driven trend in the networking industry to build and encourage open standards development. Open networking aims to improve networking by providing an open source basis for network operating systems and a community-driven paradigm for continuous improvement, which is closely tied to the ideals of software-defined networking and DevOps movement. So the term open, right, can relate to a variety of ideas, including open source software, open API support, and open protocol standards. And as a result, there might be a wide range of methods for establishing openness to serve varied purposes. The open source software movement has several goals. First is to access to the underlying network operating system, or NOS, is unrestricted. Participation of the community is an ongoing improvement. The application of open APIs and open protocol standards which are being supported. Some examples of open networking software projects are shown here. The following are the descriptions of these open networking software projects. First is OpenFlow, which is a low-level protocol for manipulating a switch's forwarding table. We have OVS, or the Open vSwitch. It's just like a virtual switch that is typically used in conjunction with hypervisors to connect virtual computers on the same network or across network. Next is a CompTIA. So here, infrastructure operational policies for container-based applications deployment are being defined in several projects. Next is OpenStack, Neutron, right? So it is a software-defined project aimed at providing network as a service in multi-tenant and virtual computing environments. We got I/O, or FD.IO, which means fast data input-output. It's actually a collection of projects and libraries that enhance the data plane development kit, or DPDK-led revolution, to allow flexible and programmable and composable services on a generic hardware platform. Cisco supplied the VPP library, or the Vector Packet Processing Library, which is a major component. The code is currently being used in terms on the market, right? And the VPP library is designed to be highly modular and allows additional graph nodes to be readily plugged in without requiring changes to the underlying code. It also allows developers to quickly create a variety of packet processing systems with different forwarding graphs. And the last one is Open Daylight, which is a collaborative initiative that aims to promote and organize SDN adoption through a community-driven approach. Okay, so a programmable infrastructure is defined by the ability to automate and script network tasks. So as shown here, right, there's actually two types of network programmability. First is on box, and the other one is off box. Okay, so what's the difference? On box programming refers to the scripting techniques such as TCL or TCL, tool command language, right? Like this one, or the embedded event management or manager EEM, which is both or which come pre-installed in the network operating system of several Cisco products like the Nexus switches. A native Linux interface is available on several platforms, as well as access to a Python execution engine that can be used to improve on-box programmability. In most cases, on-box techniques are platform-specific. Now, there's also scripting methods that reside outside of the network device, which are referred to as off-box programming. It can take the shape of an external controller, right? It's actually here, right? A box. So it can take shape of an external controller or a server that communicates with the network device via APIs that are both robust and current. Some examples are netconf, restconf, or rest as well. And what else? Well, all of these are examples of these APIs. Okay. Some additional concepts, right? SDN refers to a set of strategies rather than a specific technology for programming network devices via network controller or some other network mechanisms or external mechanisms. The ability to monitor, manage, and modify network behavior dynamically using an open interface rather than through closed block approach is referred to as SDN. It allows the network to be controlled as a whole and improves the network ability to be configured in a more deterministic and predictable manner. So earlier, right, I said SDN was first associated with OpenFlow, but it quickly expanded to include additional architectures, designs, and concepts for changing and re-architecting and managing networks to better allow business operations. So in terms of SDN industry trends, right, SDN employs numerous principles as part of the current industry trend. First is the separation of control plane and the data plane, as I've said earlier, right? So this separation of control plane and data plane of a network device, right? The tendency to separate the control plane and data plane of a network device focuses less on the protocol utilized, which is typically open flow, and more on the business value separation brings. Number two is software-only network virtualization. So here, solutions that use a native software-only method to create overlay tunnels across hypervisors in the data center are known as software-only network virtualization. Now, while these technologies provide some flexibility for the virtual network, physical workloads are still mostly unintegrated, and as a result, there are frequently performance constraints. Three is NFV, or Network Function Virtualization. This is actually a widely used technique that virtualizes all network functions. Firewalls, load balancers, intrusion detection and prevention devices, routers, and sniffers are examples of virtualized network appliances. And fourth one is disaggregation. Now here, a bare metal switching platform based on Linux NOS is being promoted by several companies. When network providers such as Cisco use more merchant silicon, there is frequently less advantage to employing a bare metal or white box approach, especially when compared to industry-leading Cisco hardware and software solution. There's also a trend about device APIs, right? So as we know, APIs are now supported by practically every Cisco network device. The Cisco iOS XE devices, for example, now support netconf, but Cisco iOS XR devices support netconf, restconf, and gRPC. NX API is supported by Cisco Nexus switches, while REST is supported by Cisco ACI. The Cisco Application Policy Infrastructure Controller Enterprise Module, or APKM, and Cisco ASA firewalls. REST and RESTconf are also supported by the Cisco Open SDN Controller, or OSC. Now let's talk about DevOps. So DevOps is a new paradigm in IT procedures that has been gaining traction in recent years. Its core objectives cover the full software delivery pipeline, specifically increase the number of times software is deployed, reduce the time it takes for a product to reach the market, and reduce the number of new releases that fail. So the DevOps culture supports an incremental approach to software development, release, and continuous improvement, preferring the agile methodology. Developers and engineers take tiny incremental actions to solve one problem at a time. So DevOps integrates DevOps teams, right? Functions and systems within a company using what we call as COMS here, which means culture, automation, lean, measurement, and sharing, which then encapsulates the main ideals of this approach. A company's culture is the most important factor to consider when implementing a DevOps method to managing infrastructure and apps. So here, DevOps culture is typically defined by values such as trust in the workplace, respect, collaboration, goals that are shared, being a good friend, of course, and there's a perception that there is no one to blame or that there are no victims on this one. So DevOps offers a different type of information flow, such as working in the open, and managers tend to want the opposite of a top-down manner of team communication. Engineers should be able to inquire and respond while work is being performed in the first place. Here are the examples of tools used by DevOps or a DevOps culture to allow a strong deployment pipeline, right? And all of these are included on this table. So as you will see here, we have several operating systems, which is Linux, Debian, Red Hat, and Ubuntu. We got programming languages, which uses Go, Ruby, and Python. For configuration management, we're using SaltStack, Ansible, Chef, and Puppet. For continuous integration, we got Circle CI, BuildBot, Travis CI, and Jenkins. And the last column is about version control, which includes Git, GitHub, and Bitbucket. Let's talk about Cisco SDN and network programmability trends. So Cisco's products and technology portfolio is constantly evolving to meet the needs of growing number of automation and network services customers. The portfolio's key components are as follows: multiple tiers of NetConf, Yang, and RESTConf, REST administration interfaces, software bodies of the controller and orchestrator kind for data center use cases, infrastructures for the enterprise campus WAN and cloud, and for NFV and network service containers. Linux-based virtualization technologies are becoming more popular. So one of the Cisco SDN solution is the Cisco DNA Center, right? So here, the Cisco DNA Center represents the Cisco DNA, which the enterprise's intent-based network management and command center. Cisco DNA is a software-driven architecture that speeds up and simplifies enterprise network operations while lowering cost and minimizing risk. Cisco DNA Center is a software-defined networking controller that lets you provision and configure all your network devices in minutes, and it uses Cisco DNA software to enable features and capabilities on network devices, and all of which is managed from the Cisco DNA Center dashboard, right, which is in here. The unified dashboard combines advanced features with straightforward procedures to facilitate the provisioning of users and control. So as you will see here in the dashboard, right, it gives us a lot of insights like for wireless, RSSI, onboarding times, client health summary. So if you have a lot of users within the enterprise campus and you have a DNAC installed, you will be able to see some statistics regarding the network connectivity of a specific client. Okay. So if you have a really bad wireless network, you should be able to see it here. So it's going to be very easy to troubleshoot. Next, Cisco SDN solution is the Cisco SDA, or Cisco Software Defined Access. Cisco SDA is an enterprise intent-based networking solution based on Cisco DNA concepts. Now, without rewiring the network, it allows automated end-to-end segmentation to separate user, device, and application traffic. Now, it extends to the Cisco ACI data center as well and allows you to automate user policy access and create a single network fabric spanning wired, wireless, and IoT environments. Cisco DNA Center delivers policy enforcement, right, and workflow-based automation and user and application activity analytics. And furthermore, the Cisco DNA Center controller offers northbound REST based APIs to enable third-party or internal development of network-relevant services. So here's another Cisco SDN solution, which is called SD-WAN, or well, they call it Viptela, right? So Cisco SD-WAN is a cloud-delivered architecture. It allows you to securely connect any user and any application via WAN or wide area networking using a single administration panel called the Cisco vManage. And as well as connect them to the cloud platforms with increased speed, reliability, and efficiency without compromising security. Now, to increase network performance, security, and efficiency, you can rapidly set up an SD-WAN overlay fabric to connect data centers, branches, campuses, and colocation facilities. Cisco SD-WAN analytics identify connection and contextual issues after creating templates and policies to determine optimal paths for users to get their destinations independent of their connectivity. So another kind of Cisco SDN solution is Cisco SD Branch. So with software and hardware designed specifically for branch deployment, you can deploy, monitor, and optimize network services. Cisco VNFs, which deliver trusted network services as software, including routing, firewall, application acceleration, and wireless LAN controller software, as well as third-party services, replace various tasks formerly available as distinct hardware appliances. Now, the Cisco DNA Center allows you to manage SD branch solution and automate network service provisioning across the entire network on any hardware or virtual platform. The Cisco SD branch, right, delivers on-demand network services, allowing adding new services and updates easy without travels to remote locations, and enables you to install business-critical services in minutes. And thanks to the centralized orchestration and administration for SD-WAN and traditional routing infrastructures. Okay, now let's talk about network programmability and automation. So as you may be aware of, right, network operation is built on human contact with network devices. Network experts set up one device at a time using Notepad and one of the most used text, or actually Notepad is one of the most used text editors. Now, when functioning at scale, it causes a slew of issues, right? First, CLI was built actually for human interaction with setup speeds limited to the speed at which the person can work. Second, when configuring several devices, manual configuration and conventional copying and pasting procedures are particularly prone to error. And third, jobs are difficult to repeat, resulting in inefficient processes. So, network engineers can execute more optimal workflows, right, by leveraging tools that are often used in software development, such as employing version control systems to store network configurations. Configurations are versioned and tracked in this manner, and they also used as the source of truth. Furthermore, any change that is accepted will be thoroughly checked with automated software to guarantee that one or more changes are valid. So for a variety of routine tasks, network automation is deployed, right? And the following are the few of the most common tasks. First is device provisioning. So here, when engineers think of network automation, one of the first things that comes into mind is probably device provisioning. Because human contact with each network device is reduced, device provisioning simply means configuring network devices more efficiently, faster, and with fewer errors. Next is data collection and telemetry. So here, collecting data from network devices and telemetry on network behavior is a common aspect of properly maintaining a network. Even the manner the data is collected is changing, as many devices, such as iOS XR devices, now have the ability to push data off the box in real time, rather than being pulled every 5 to 15 minutes. Next is compliance checks. So here, network automation methods provide the unique ability to quickly audit large groups or network devices for configuration issues and make the necessary repairs automatically using built-in regression tests. And the last one is reporting. So here, automation reduces the time and effort required to collect information and coordinate data from multiple sources in order to produce meaningful and understandable efforts. So right here, right, network automation, of course, it simplifies troubleshooting by making configuration analysis and real-time error checking quick and easy, even with a large number of network devices. So several open source and commercial technologies that were previously used to automate system operations are now being used to automate network operations as well. Systems operation teams have been using a combination of commercial and open source solutions to automate virtual environments and workloads and develop a completely programmable infrastructure for several years. So, commercial platforms like VMware, vCenter, Microsoft System Center, and Citrix Send Server, as well as open source approaches like Ansible, Puppet, SaltStack, and Chef, have been utilized and are still being used by sysops. Today, network operations teams who have realized the value of programmable infrastructure are employing some of the same techniques to manage their networks. The Cisco portfolio includes numerous systems that network operations teams can employ, which includes Cisco ACI, Cisco Open SDN Controller OSC, Cisco um, WAE, Cisco NSO, and Cisco APIC EM. Okay, so to automate and manage the entire infrastructure, network operation teams can use the Cisco tools in conjunction with existing open source methods such as Ansible, Puppet, SaltStack, and Chef, right? And they're all based on Linux and use Python and Ruby as their programming languages of choice. Now, there's also a lot more network programmability than having programmatic interfaces on network platform or network devices. When adding network programmability and automation into a particular context, a variety of methods are used. So, when introducing network programmability and automation, you must examine several issues and associated technologies, just as you would with traditional programming, such as Linux, right? Which is the operating system of Linux. It is the foundation of everything, as you may know, from version control to programming languages and configuration and management tools like Ansible and Puppet. Linux is nearly always the operating system of choice. So the first one is Linux, right? So the operating system Linux is the foundation of everything, from version control to programming languages and configuration management tools like Ansible and Puppet. Linux is nearly always the operating system of choice. Next is version control, right? So using a system like Git, everything should be versioned. It's much easier to exchange and collaborate on projects containing everything from code to configuration files when you use a platform like Git. Okay. And software development here. So while not every network programmability engineer will be a master programmer, understanding software development processes and how software development may be utilized to extend or adapt to open source technologies is essential. Next is automated testing. So it's an important aspect of network programmability, right? And the predictability of determinism of network resources are improved by automating adequate testing, such as pre and post change on the network. And you should have automated tests that execute under specific situation or whenever a change is being proposed. Next is a continuous integration, or which is the CI in here, right? This means continuous integration. Like many of these tools and technologies, is widely used by developers and may substantially improve the release cycle of not only software, but also network configuration modification. CI tools and pipelines can aid in the execution of your tests, allowing them to run as changes are submitted using version control tools. Now let's talk about Cisco platforms and APIs. So here, right, the API allowed Cisco network devices to move away from on-box programming and toward off-box programming, right? So as you will see, the table below lists the various Cisco platforms and APIs that go with them. Most Cisco platforms now include an API that allows for the off-shelf programmability. The specific API depends on the platform, but as time goes on, you'll see more open methods and platform uniformity. So to provide network operators with off-the-shelf programmability, various Cisco platforms leverage a variety of APIs. So for iOS XE, right, devices like the Cisco CSR 1KV, ASR 1K, I'm just gonna put it here. Okay. The Catalyst 3850. These guys use the netconf and restconf. Okay. Now for Cisco iOS XR devices like the ASR 9Ks, right? If you're familiar with this device, this these are the APIs available, right? To communicate to the API, you need netconf, restconf, and gRPC. Um, Next is for Nexus, right? We call it the NX API. It's in here. So this is available, NX API, CLI, REST, and netconf. What else? For the REST, right? For the other for this other Cisco platform, we can use REST, right? Representational state transfer, REST. Well, honestly, the easiest API that I can use is REST. Right? Because you can just download like a software like Google Postman, and you can use REST from there and be able to communicate to these devices. Let's just talk about some tools that is being used in Cisco network security, like FMC, or the Fireside Management Center, or Firepower Management Center, FMC. So it's actually a lightweight API for managing a Cisco FMC. It is being provided by the Cisco FMC REST API. You can use a REST client to rapidly enable REST API on any Cisco FMC running version 6.1 or higher. Here, you can call the specific FMC's REST agent and use normal HTTP ways to get current configuration information and issue new configuration parameters after installing a REST client. Right? So this is the Cisco FMC REST API. Now, because the REST API in Cisco FMC has a variety of objects, you can use the API Explorer, right, to familiarize yourself with the API. It includes limited interface for the REST API, as well as the list of FMC APIs and their description. So the API Explorer is located on the FMC and actually can be found using this particular link, right? This one. The Open API specification was used to create a new API Explorer in version 6.4. Although the newer API Explorer retains nearly all the previous functionality, the legacy API Explorer is still available if you prefer. The Cisco FMC and the REST API both use the same authentication mechanism. As a result, you'll need appropriate permissions in the Cisco FMC for each function you implement using the REST API. You can log in to the API Explorer with any Cisco FMC account, but you'll only be able to use the functions that the account has access to. Any REST API client can be used to access the Cisco FMC REST API. REST API clients are typically available as browser plugins, but any REST API client is acceptable. If you connect to the REST API for the first time, you may receive an error message stating that the connection is not secure due to invalid certificate. So here you have to make a browser exception to use the certificate and accept the connection. Next is a token-based authentication is used for REST API access to the Cisco FMC, which allows you to obtain a token by providing your username and password. This one-of-a-kind access token is then used with every HTTP request for a set of period of time, obviating the need for a username and password. Authentication tokens for Cisco FMC REST APIs are valid for 30 minutes and can be refreshed up to 3 times. Now, to request an authentication token for the REST API access to the Cisco FMC, you gotta perform the following. First is you open your REST API client and set the client to make a post command using this particular URL, right? That's one. And here you got to include the username and password as basic authentication header. Then the post body should be blank. Now in the response, you can find the XAuth AX token, which you can add in the header of the request that you make to the API. You can also use the domain UUID from the authentication token, which is the domain universally unique identifier or UUID in all REST requests to the server when needed. So requests are sent to the Cisco FMC as HTTP request using the following URI, right? This one, use this, where the management center IP, this one, is the IP address of the FQDN or the fully qualified domain name of the Cisco FMC. Then the HTTPS port is the port number used by the Cisco FMC for HTTPS connection. And well, normally it uses 443, right? Should be 443, which should not be supplied in the URI. And the object URL is the specific URL for the desired resource. And these URLs are unique for each resource. And we got the UUID here, right? Well, here we got many URLs that contain one or more UIDs, which must be specified. Most URIs include the domain UUID, which can be found in the authentication token. And when deleting or modifying an object or requesting information about a specific object, the URI will end with the object UUID. And the last one here is the option here. Which are the options given with the request. Options can be used to modify the output and filter results. So when you use REST, right, here are the available request methods, which is the get, right? So which means that it's just a read-only operation to retrieve data from the specified object. You have a put, which adds the supplied information to the specified object and returns a 404. Okay, resource not found error if the object does not exist. Next is post. It creates the object with the supplied information. Post operation should be followed with a payload consisting of a JSON object to be created enclosed in braces. Delete, which deletes the specified object, and patch, which is not supported. You can use the REST API to retrieve system information from the Cisco FMC with the following parameters. So as an example, right, you can use the get as a request type, put the description, and put the URL that looks like this. And you have to set the permission. So each response includes an HTTP status or error code. Like for example, 200, right? 200. Okay, indicates the standard response. Indicate standard response for successful request. If successful, the response body will provide the Cisco FMC system information that looks like this that can be used further for different purposes. And here, as indicated in the following output, right, which is represented in JSON format. Okay. Now let's talk about Python scripts and APIs. So Python is a powerful, right, and easy to use programming language. It is an ideal language for scripting and rapid application development because it has efficient high-level data structures and a simple but effective approach to object-oriented programming. Python is an ideal language for automation and management because of its elegant syntax and dynamic typing, as well as its interpreted nature. Because the Cisco networking product line supports Python, you can use it to edit and modify existing scripts as well as create new ones to automate Cisco networking tasks across the enterprise. The Python interpreter and extensive standard library are available for free on the Python website, which is this one, in source or binary form or all major platforms. Many Cisco switches and routers include a Python interpreter and can be used to run scripts and programs on end devices directly. In addition to the interpreter, the device have Python libraries that give them direct access to the device's operations, allowing them to run CLI commands or watch for events. Like for example, you can use the device to run a single CLI command or a or a batch of CLI commands. Python scripts can also be used to interact with external APIs of various Cisco platforms such as netconf, restconf, and REST, and so on. For example, you can also use Cisco Python script to retrieve data from a Cisco APIC EM, right, via REST API. So now let's talk about the Cisco FMC and Python interaction. So the Cisco FMC REST API lets you automate tasks like retrieving audit records, creating objects and policies, and registering devices. Because Python scripts can interact with the Cisco FMC REST API, you can use object-oriented programming to perform the same network automation tasks. You can write your own scripts or look for a collection of tools or common tasks on the Cisco FMC at https://github.com. As a result, you can find the repository of Python scripts to perform some routine change faster, which is usually time-consuming when using the Cisco FMC GUI. You can use the Cisco FMC Legacy API Explorer to create your own Python scripts. When you select an API and use one of its request methods, you can use the export operation in button in the Legacy API Explorer's API console section to quickly report the displayed method example in scripting language. Methods can be exported in Python or Perl scripts, right, as shown here, using Legacy API Explorer. This script can be used to make the REST call and integrate it into your app, and this is primarily intended as a learning and bootstrapping tool. So the following are the contents of the Python script that uses the Cisco FMC REST APIs, right? So this is the whole code. This is the whole code, right? And this part in here, right? I just zoom it in. It's going to show you the required libraries, which is this, and the FMC IP address, or you can put the host name. Okay, so that's the first part. Then you got the username and password for authentication, right, in here, which is at the beginning of the code. And you have the code for code generation of the authentication token in here. And next is you have the actual request body, right, or the REST API. And after this one, you should be able to get the status code, right? So there's a lot of codes there. If you see a 200 OK, then you should be able to receive the one that you're trying to get, okay? So this is the end of the lesson. Here we covered SDN concepts. We also discussed network programmability and automation. We talked about Cisco platforms and APIs, and we discussed about a sample Python script that is being used to communicate to the Cisco Firepower Management Center, or FMC. Thank you very much for watching the video.